Okay, I think we should let everyone in. Is it safe to just click admit all, which I just did? And we'll start in a minute. So everyone, welcome. Welcome to today's SAZERAC. It's a two-day event. Great. And I think people will keep trickling in within the first few minutes and counting. Great, I'm very happy with the turnout. All right, we can wait for another minute or two. We have time. Hope everyone's doing well. Okay. So if you're not already on the Slack channel, there is a Slack channel for dedicated Slack channel for today's and tomorrow's SAZERAC SIP. So do join it, and you can ask questions there. And I'll go over the logistics in just a bit. Will, can you take over and start admitting people as well? I might start going over the logistics in just a bit.
Yeah, no, that's fine. Don't worry about any of the tech stuff. I've got it.
Thank you so much. All right, so this
under control.
Great, thank you so much, Will. This is 10:01, and I think we should kick things started a little bit. So thank you everyone for joining us. This is a strange time that we all kind of feel that Zoom fatigue, and I'm still super happy that all of you are here with us. So we're still waiting for in-person conferences to happen, and I still hope that we can someday make it, into the same room together and get to talk face to face and hang out in the coffee hallway or something. But as for now, this is the best we can be, gather to discuss our favorite science and enjoy the comfort of your couch. So jokes aside, I'm in the office now. We think this is very important to give these channels open. So the junior scientists, folks, career just started like myself, would not be completely doomed by the pandemic, and will have a chance to tell everyone about their science as a way to promote their work, or just as practice is fine. We can only do good. So just want to quickly shout out and thank my amazing SOC, Eric, Chris, Ashwin, and Will is helping out with Zoom and YouTube today. And I left Steve. Yeah, Steve is also on the SOC, yes. Steve is with us, and not today because he has an emergency departmental meeting, so bummer. Right, so now I just have a few more logistical things before we dive in. The talks are happening live on Zoom, but if you're joining us from YouTube, there might be a slight delay. So I encourage everyone to just type in your questions into the Slack channel before before the talk ends as they come up. So when you have a question, just quickly type it in. Don't wait till the end. And even though your question doesn't get answered live, we still encourage the speaker to go answer them afterwards. And for the sake of time, I will have the section chair read the question out for you. Hope that's okay. As always, please adhere to the SAZERAC Code of Conduct during the conference. We actually do have one, so do check it out online in the SAZERAC website. I'm not going to read them all out. So I'm going to turn to my SOC and ask, did I miss anything? I think that's pretty good. Okay, so we still have a few minutes to spare. I just admit, but I think we can just kickstart the talks. Okay, so first up in the schedule, we have a plenary talk by Rahul Kannan, who is at the Harvard ITC now. So I will turn it to Rahul, and just tell us about galaxy formation and modeling at high-redshift.
Okay, thanks, Aaron.
Just for that, I'll give you a 5-minute warning, I guess, with this guy.
With the wine glass, sure.
Yes, very classy.
Let me just check if everything is working. So can everybody see my screen?
Yes, I can see it.
Okay, good. Yeah, thanks, Aaron, for giving me this opportunity, and all the organizers, of course, for giving me this opportunity. to give an overview talk at this really exciting conference. And of course, I will mention that it's not possible to give a complete overview in half an hour. So I might miss some points or extremely nice work that people have done previously. So if I have missed something really important, then please let me know and I'll make changes. So the idea is that I will just give a general overview about why models and simulations of high-redshift galaxies are important, and also the necessary ingredients in order to model this epoch. Okay, so let's start. Okay, so what is the high-redshift universe? Of course, there is no particular definition. We generally consider, well, at least for this conference, we generally consider the high-redshift universe to be anything about redshift 6. So you can divide this high-redshift universe into two phases. That is basically cosmic dawn and epoch of reionization. Of course, the distinction between these regimes is not fully understood. It's not clear, but generally speaking, cosmic dawn is just the first, is the time when the very first stars and the proto-galaxies formed. And the epoch of reionization is generally considered to be when these galaxies start affecting their immediate surroundings. That is basically when you have these early stars and galaxies, they start emitting large amounts of Lyman continuum radiation that ionize the neutral gas in the universe, and that phase transitions the intergalactic medium from a cold and neutral one to a hot and ionized phase. And the reason why this high redshift is important is because it is an important evolutionary link between the smooth distribution that you see in the cosmic microwave background and the clumpy universe that you see currently. So, so it's a very important evolutionary link between the high redshift, extremely high redshift, and the low redshift universe that we see today. Okay. Why is studying the high redshift universe timely? Well, there are a few important developments that will happen in the near future. So JWST is about to be launched, and it will be a game changer for this field. It has a much larger mirror than Hubble, for example, and it also has a larger frequency coverage, especially in the IR. So this these larger mirror and the larger frequency coverage will provide enough sensitivity to detect even the low mass galaxies at these high redshifts. And the spectroscopy from JWST will allow for accurate characterization of the star formation rate, stellar mass, metallicity, and even the ionization state of the ISM. And the launch date is, of course, December 18, and let's hope that all goes well. And we already have ALMA, which has already been detecting high redshift galaxies. For example, here I show one of those detections from Nature paper where they detected cold ISM of a galaxy at redshift 9. And ALMA mainly detects the cold phase and the dust in these high redshift galaxies. For example, the C2 line and the O3 line, just as an example. Okay, so then this slide, which I borrowed, basically quantifies what I said in the previous two slides. So these are basically like the detection limits as a function of star formation rate for JWST near spec, JWST MIRI, and ALMA. And the signal to noise and the integration times are given on top here. So JWST is very sensitive to unobscured sources and mainly UV and optical lines like H-alpha and O3. Whereas ALMA probes the lines which are insensitive to dust and IGM absorption, like C2, for example, and CO. Of course, oops, go back. Yes, of course, as you can see here, there are limitations. For example, at redshift 6, above redshift 6 or so, you can only detect galaxies which are star forming, in the sense the star formation rate is greater than 1 here. You cannot detect the really low mass stuff even with these very nice instruments. So for that, we have something else which is coming online, which is already online and coming online soon as well, other instruments, which is basically the line intensity mapping technique, which is, it measures the spatial fluctuations in the integrated emission, which from the spectral lines, which originate from many unresolved galaxies. That's what is shown here. On the left is the galaxy population. On the right is pointing the galaxies. On the right is a mock line intensity map image. I think this CO, I'm not sure, but the point here is that this technique is sensitive to almost all the sources of emission in the line, depending upon where your sensitivity limit is, of course. But it is quite important technique, because while galaxy surveys probe discrete sources that are bright enough to be detected, the line intensity mapping will give you all the emission in that line, in the whole volume that you're probing. So that's one way of detecting, very important way of detecting all the high redshift galaxies. So there are a lot of current and upcoming line intensity mapping experiments. Here, this plot just shows a few of them. Well, almost all of them, I suppose. So there's a line intensity mapping of 21 centimeter, which is basically, the spin-fit transition of neutral hydrogen, which is, so this kind of gives you the tomographic image of the neutral gas in the universe. And as reionization progresses, with enough sensitivity, you can even detect the bubbles and the bubble size distribution using this 21 centimeter technique. Complementary to the 21 centimeter, you have intensity mapping of, for example, the middle panel, which shows the C2 and CEO lines. Things like COMAP and CCAT prime are trying to detect these lines in high redshift galaxies about redshift 7. These trace the molecular and the photo dissociation regions in the ISM of galaxies. And you also have stuff like SphereX and the cosmic dawn intensity mapper, which tries to map the UV, rest frame UV lines, UV and optical lines like H-alpha, H-beta, and O3, and also Lyman-alpha, for example. So these three all put together, you can get a full tomographic picture of the matter distribution in the universe, and also the reionization process and the sources that are galaxies and black holes that are responsible for it. So it's a very powerful technique. Okay, so I kind of talked about why. So why is it exciting to study high Z galaxy formation in AOR? So the question is, how do we do that? So there are many different models which study this high redshift universe. I'll start with a very simple but very powerful class of models called semi-empirical models. They're also called abundance matching models, for example, where you match the properties of dark matter halos. Usually, these dark matter halos are derived from a dark matter simulation, to the observables, to the current observational constraints, using some kind of a scheme. There are very different ways of doing this, of course. Here I just show one method of doing this from Peter Berrosi's recent paper, which describes this in detail. Of course, the problem is there are no physical prescriptions for the processes, so the physical reasons behind the derived relations is not always clear. But it is still quite a powerful method to do this. Okay. Then there is another class of models called semi-analytic models, where they take the same dark matter halos from these simulations, from dark matter only simulations, and then use phenomenological physical prescriptions, for the physical processes arising in these galaxies. For example, there is physical prescriptions for gas accretion, physical prescription for star formation rate, physical prescription for supernova feedback, and etc. and etc. Of course, it is very computationally efficient, and therefore, using these class of models, you can probe a wide range of the parameter space in galaxy formation reionization. And I give some examples here, not a complete exhaustive list, but some of them. The next class of models is semi-numerical models. These are mainly used to simulate reionization. So, for example, 21 centimeter fast, or Astraeus by Ann Hutter, who is going to be talking next. So basically what they do is either they use LPT or semi-analytic models or hydrodynamic simulations and post-process them with full coupled radiative transfer or semi-numerical radiative transfer in order to model the reionization process. These are computationally very efficient because because most of the prescriptions are either semi-numerical, so you don't need to solve the full coupled equations. So it's very computationally efficient, but you still require inputs from full-scale galaxy simulations, like for example, gas clumping factors, self-shielding to the gas, photoheating prescriptions, etc. And finally, there are numerical, fully coupled numerical simulations, which are basically follow the dark matter dynamics, gas dynamics, radiation hydrodynamics, and even magnetohydrodynamics self-consistently. Of course, it's very powerful in the sense that if you have infinite resolution, you can simulate anything from first principles, but in real world, that does not happen. So what happens is that you need some kind of subgrid prescriptions to model the physical processes, like, for example, supernova feedback or radiative feedback that happen below the grid scale of the simulation. So what these subgrid prescriptions do is they kind of mimic the process that happen below the grid scale of the simulation and put an effective description of it onto the grid scale. And of course, again, these are some of the examples here. Okay, good. And since I'm basically, I mainly deal with numerical simulations, I will, for the rest of the talk, I'll focus on this particular method and then continue. So, so what are the ingredients to model galaxies or high-redshift galaxies? I take this from Mark Vogelsberger's recent review paper, where he lays out a few important processes that are important for sculpting galaxies. For example, gas cooling, modeling the interstellar medium, star formation, stellar feedback, black holes, black hole formation and feedback, magnetic fields, radiation fields, and dust. So why is gas cooling important? Of course, it is. That's the only way the gas loses. That's the way the gas loses most of its energy, by radiating away its energy in the form of from radiation, basically. But it is a complicated process to model because you need to know the chemistry of all the elements that are in the gas, not just hydrogen and helium. As soon as you get a little bit metal enriched, you need to model, for example, cooling from iron, carbon, and even from molecules like CO and H2 and stuff like this. So it's very complicated to model all of this self-consistently. So instead, what most of the simulations do is they use tabulated cooling tables. So they use something like cloudy, and they pre-compute this cooling as a function of density and temperature, etc., and then use that cooling table in the simulations. Now, if you want to understand why it is important to do this at high redshift, then the point is at high redshift, you will not have enough metals or dust. So many of the cooling channels which are important at low redshift will not work at high redshift, for example. So you need to require accurate primordial networks, metal and dust-free networks. So I highlight talks from Sean Barrett and David Robinson in this conference, who will talk about these things. So on the right here, I show one of these examples from a very nice paper by Thibault Garel, where he shows like the pressure, the ISM pressure curve as a function of density at high redshifts here and low redshifts here. At high redshifts, you can have 3 different densities existing at the same pressure. So you basically get a multi-phase ISM. But at low redshifts, because of the lack of metal coolants, you will no longer get a multi-phase ISM, especially at very low metallicities. So there are important differences which exist, which arises because of the different gas cooling rates. And so it's important to understand this and model them properly if you want to understand high redshift, low metallicity gas cooling. Okay, so the next is the ISM. It's one of the most important parts for modeling galaxies, because a number of processes can affect how the interstellar medium of galaxies evolves. So there are many models like the multi-phase, like the effective equation of state model from Eagles and Illustris, and there are many models currently which also model the multi-phase ISM. For example, the phase-space density, the cold and dense phase of the ISM is modeled, but then you need higher resolutions because you need to at least be able to partially resolve this cold and dense phase of the ISM. So it's much more computationally expensive. Then there's star formation. Well, in most simulations, we do not have enough resolution to resolve individual stars. So you model the stars as single stellar populations. Most simulations use constant IMF, but there are simulations which vary this, of course. For high Z galaxy formation, it is important to model, for example, population 3 stars, which form in very low metallicity environments. And to understand their chemical enrichment, if you really want to model cosmic dawn in these models, for example. And recently there has been a push to model individual stars in very high resolution galaxies. They can probably do a simulation of a dwarf. So here I highlight recent work by Thales Gutke. And there's also a talk by Jennifer Reed who will talk about this in this conference as well. Stellar feedback, of course, this is the most important part of simulations because, well, they control most of the properties of the galaxies, at least in the low mass regime. And by low mass, I mean below L star. There are lot of different models which model different models to do supernova feedback in galaxies. There's effective feedback models like Illustris, Eagle, and Thiessen, which kind of just the effectiveness of the supernova is tuned to match the observables. So that's the way they do it, and they get a lot of galaxy properties right. But there are other class of models which have come up recently, which use results from higher resolution simulations. For example, the amount of momentum boost, as a supernova goes off in the set-off Taylor phase, and input it as a momentum feedback. For example, fire, Sphinx, and smaller models. The next is black holes and AGN feedback. Of course, this is very important at low redshift because they are believed to be the major contributors to quenching of galaxies. Of course, how the supermassive black holes are seeded is still not known. But there are also evidence that these black holes might affect low mass galaxies. So I highlight Sophie Goodman's talk in this conference here. They might also be able to provide enough radiation to reionize the universe, although this is also still unclear. There have been some works which say this, but they're definitely responsible for the helium reionization. And I will highlight a talk by Maxime Trebitsch in this. Okay, then radiation fields. Of course, this is also a very important factor in galaxy formation. During reionization, radiation can quench galaxies, the low mass galaxies. Radiation from massive stars can act as an early stellar feedback mechanism. And it also controls the phase structure, the temperature density, and the ionization structure of the ISM. And it also, the radiation field intensity in the ISM also controls the emission line luminosity from these galaxies. And I highlight a few works and a lot of talks like Daniel Ceverino, Katz, which was in this conference. And finally, the last component I'll talk about is dust. So dust is quite important because for most of the bright galaxies, most of the emission that you see in the optical and UV is attenuated by dust. And you really need to know the abundance and the grain size distribution in order to model this properly. The reprocessed IR radiation from dust can also act as an important tracer of star formation. And I highlight a few of the talks that will talk about dust at this conference here. Okay, so I'll switch now and just talk about one of the projects that I have been involved in, trying to understand high-redshift galaxy formation and Epoch of Reionization, which is the Thiessen project. And I just show here at the bottom that, well, we have a certain prescription for almost all the components that I described previously. They might not be the best prescriptions, but they give us the best description of the highest universe that we currently know of. Okay, so what's the Thiessen project? They are large volume reionization simulations, large volume 100 megaparsec, high resolution, such that they can model atomic cooling halos throughout the simulated volume. It includes a well-tested illustrious TNG and a galaxy formation model with RFO-RT, radiation-hydrodynamics, and an empirical dust model. So first results, we get, for example, one of the most important tests for reionization simulations is to get the reionization history correct. And so that's what is shown in this plot. It shows the neutral fraction evolution as a function of redshift compared to observations. It's not important to understand different models here, but it is good to show that we have like 6 different reionization models, and all of them kind of match the observed evolution. And we also get the right stellar properties. So here I show the baryon conversion efficiency, that is the stellar to halo mass relation as a function of halo mass. So the blue points are the Bernoulli curves. The red is Stefanon observational results. And this is pink is Sphinx, and this is FirstLight. This band is the abundance matching, kind of abundance matching from Takela. And these are the Kroc simulations. So we show that we kind of match the Bernoulli 2019 abundance matching relation and broadly in agreement with Stefanon. Other simulations like Sphinx and FirstLight kind of seem to have too high baryon conversion efficiency, and Kroc at high masses seem to have low baryonic conversion efficiency. We also match the UV luminosity functions here at redshifts 6, 7, 8, 9, and 10, as long as we use a dust attenuation model, which kind of works. So our internal dust model in the simulation does not give enough attenuation, so we had to use a scaling relation provided by folks 20 here. And we also show that in a high resolution simulation, we simulate up to the UV luminosity function matches what the Barnes 2017 estimates, whereas at lower resolution, then we match the turnover as shown by observations from Katz. Okay, so what we can do, because we self-consistently simulate the galaxies and the reionization process itself, is we can model the emission lines and the 21 centimeter elevation from the same simulation volume. So we model emission lines, for example, like H-alpha, O3, 88 micron, and C2, 158 micron, by painting on H2 regions onto Thissen galaxies, and we get the right stellar edges and metallicities are modeled self-consistently. We also model the gas and metal content, and we use a grid of cloudy models to obtain emission line luminosities from H2 regions, and then use SCRT to calculate the dust attenuations. So what we actually get is from this is high resolution SED of galaxies in the simulation volume. So the blue is the intrinsic SED, and the red is the dust attenuated SED. And then we show particular important UV and IR lines that will be observed from GWST ALMA and the line intensity mapping techniques. So we do this for the whole simulated volume in Thissen. And then what we can do is plot the scaling relations. So the luminosity versus the star formation rate for all these different lines, and compare them with observations. And we show that these relations, although they are generally correct, there are important differences between the observed low Z relations here and the high redshift ones that we derive here because of the difference in the metallicity of the ISM of galaxies. And once you have this luminosity star formation relation, you can create line intensity maps. So on the top, you have the intensity map of the 21 centimeter, then H-alpha, O3, the UV, 5,000 angstroms, 5,700 angstroms, and O3, 88 micron angstrom. So from these intensity maps, you can kind of cross-correlate the 21 centimeter emission and the line intensity emission to get this cross-correlation function. And the position of the transition wave number kind of tells you where in the reionization process it is. And also the different models. For example, this is a model, the orange is a model with only high mass galaxies contributing, whereas the green is a model with only low mass galaxies contributing to the reionization process. So these models, looking at the transition wave number as a function of neutral fraction, you can actually differentiate between the sources that are responsible for the reionization process. So the line intensity mapping and the cross correlation between the 21 centimeter and the nebular emission lines can help you constrain the sources of reionization. Okay, so I'll finally end here with a few future directions and model improvements that are, I think, important for us to understand galaxy formation and high redshift. So as I said before, it's an exciting time to study high redshift galaxies. JWST is coming online. ALMA is already taking very nice observations. You have 21 centimeter intensity mapping experiments, and within a couple of years or so, they claim they will be able to constrain the power spectrum, and not just the upper limits, but provide a value at K of 0.1 to 1 or so. And you also have intensity mapping of nebular emission lines. So with all of this put together, we will be able to trace galaxy formation and reionization in unprecedented detail. So in order to understand what these observations mean, you need realistic galaxy formation models. We do have some, but we need improved ISM and feedback models. For example, you need to get an accurate multiphase structure and correct stellar masses. You need to understand how the structure of ISM is in low metallicity environments, which was not previously done before. There is a need to include POP3 stars, enrichment, and primordial chemistry. If you want to extend the modeling to cosmic dawn, you need an increased understanding of dust physics, not just the dust masses, but also the grain size distribution. And we also need to understand black hole seed accretion feedback at these early times. The way to proceed is to use various simulation methods together. For example, you calibrate SAMs on RHD simulations and so on and so on. You also need to leverage multiple observational estimates, like for example, intensity maps of liminal lines with intensity map 21 centimeter line, which can kind of tell you about the escape fraction and the star formation rate of these high mass galaxies, which is very difficult to get from like first principles using simulations. There is also a need to go into an observer space, for example, predict the UV luminosity function directly rather than the stellar mass function. And there's also a need for multi-epoch validation. So the models need to be tested at a wide variety of redshifts and not just at a particular one in order to understand the advantages and disadvantages of the model that you're using. So thank you.
Round of applause. Thank you for the plenary talk. Great. So I think we have one question from Slack, at least the last time I checked. Let's see. Daniel, you're here actually. Do you want to just ask it yourself?
Sure. Yeah, it's about the stellar halo mass relation. When you do the comparison with the other models, do you take into account the corrections due to the different IMF and different cosmologies? Yes. Here.
So the IMF, yes. Cosmologies, no.
Yeah, because if you do that, redshift 6, basically all the Takela models and the FirstLight are very similar to the observations.
So which observations?
The Stefano et al.
Okay, yeah.
So the models move down to lower stellar masses and higher halo masses.
Lower stellar masses and higher. So what kind of why is the cosmology so different here?
We are using in the FirstLight, we're using the Darwin map.
Right.
That's why the halos are slightly smaller. So the halo mass function is different.
Okay, yeah, thanks for letting me know. Yeah, I will correct it.
Thanks. And then we have a question from Ashwin. Ashwin asked, when modeling the non-nebular line emissions, do you inform your model on the dust depletion from your semi-empirical dust model?
No, we use kind of a scaling relation given by Vogelsberger to the 2020 paper, which kind of derives the dust to metal ratios as a function of redshift. So although we do have a dust model, as I said before, the attenuation is not good enough at these high masses. So we instead use the scaling relation from Vogelsberger 2020.
Great. And there's one more from Charlotte Mason. Can you talk more about the dust attenuation correction you had to make? What specifically in the original model work at high redshift?
Yeah, so at high redshift, our dust to metal ratios in high mass halos were lower than what is necessary in order to get the right attenuation. So you can see here, this is the attenuation curve, the UV luminosity function if you use the original dust model versus if you use the scaling relation given here. So our dust model predicted dust to metal ratios which were too low at high metallicities, whereas the Vogelsberger scaling is constant throughout. So we kind of match at low metallicities, but at high metallicities, the dust to metal ratio falls over, whereas this is constant, and that is more in line with what you need in order to match the attenuated UV luminosity function at high masses.
Thank you. And we do have a live question from Andrea.
Hi, Rahul. Hi, nice talk.
Thank you.
I was wondering what, in your opinion, is going to be the most important bottleneck to prevent our ability, for example, to understand and model correctly JWST observations. So it's more on the simulation side, on our ability to observe simulations, things we can't really model like escape fraction. Just if you have an idea of what it would be.
Yeah. Oh, sorry. Yeah. So I think so. Although I have talked about, modeling these emission lines even using TSIP, right? This is the best we can do using these models for now. I think they're talked by Danielle and Harley Katz, who will talk about this more. But the the multi-phase structure of ISM is really important in order to get this emission line properties right. And the problem with that is that you can do small volumes or zoom simulations with this multi-phase ISM, but it's very difficult to do it in large volumes simulations. So I think getting the radiation hydrodynamics, so the radiation field intensity correct throughout the simulation, the chemistry correct, the dust and metal enrichment correct, and all these things put together will give you the line luminosities with JWST. And so that I think numerically it's very, very challenging to do this for a large statistical sample for galaxies. But I think we can do that. Well, there are enough improvements in the simulations to do this in the near future.
Okay, thank you.
I found my cursor. So we do have one last question from Daniel. So for the emission lines, how do you compute or calibrate the ionization parameter, which cannot be derived ab initio?
Yeah, so the ionization parameter is set to a constant value here of 10 to the -2 or so. Because as I said, this is not an ab initio model. This is you're painting on certain H2 regions onto your effective equation of, because the ISM model is not multi-phase and decent. There's an effective equation of state, so you cannot get this directly from the simulations. You have to paint on H2 regions. And for that, we rely on work from Nell Byler, who did this with these FSPS models. And the only way to calibrate this is through seeing if our SEDs, photometric properties, which I do not show here, but the photometric properties like the UV luminosity functions, the UV slope, beta, for example, and the equivalent widths of like lines like O3 and H alpha are in the similar ball kinds of observations. So that's the way we constrain it.
Thank you so much. I think that's all the questions. So I know we have 4 minutes in hand because we started a few minutes early. So Rahul, once you stop sharing, I suggest that we do a conference photo. I know it's an odd time, we just started, but just in case later people may try to pop in and out, I think we should do it now. We have really good turnout. So if I may invite you to, in the next few minutes, if you can, turn on your camera. So I will take a screenshot one page at a time. Hopefully people won't shift around. Let me just make sure I know how to do that. Right, great, perfect. So everyone look at the camera, smile. Right, 1 out of 5. And 2 out of 5. All right, 3 out of 5. See if you were still turning on the camera. And we'll do 4 out of 5. All righty. Don't miss your chance. Right, and 5 out of 5. That's it. Easy. I like being a Zoom conference photographer. It's fun. All right, let me try to find myself. All right, we're back. Okay. Well, I hope everyone's having a good day. So just a quick round of advertisement. If you have not joined the Slack channel yet, please do join the Slack channel and ask questions there, because if your question don't get answered live, our speaker will still get to your question afterwards. And of course, if you find anyone's work interesting, that's one starting point to reach out and maybe start collaboration even. So who knows? Right. So we're 2 minutes ahead of schedule, but I would ask our next speaker, Ann Hutter, to get ready.
Yes. Let me share. I hope you see this all well.
Yes.
All right. Okay, cool. So yes, so I'm Ann Hutter, and I'm going to present to you the Astraeus framework, which is was built to simulate sort of the early galaxy evolution, or the first galaxy's end reionization. And so this is basically work I have been doing together with the Astraeus team. So Pratika, Laurent, Stefan, Maxime, who's also attending or giving later a talk, Graziano, and Gustavo. So I don't think I need to motivate much anymore the Epoch of Reionization. Rahul already gave like a nice introduction into this. But I think the questions we have been up to now focusing on was sort of along the lines, which galaxies have reionized the universe, the numerous faint or the sparse bright ones? What role did the escape fraction of ionizing photons play there? So versus, for instance, like if you have radiative feedback from reionization, so you have galaxies forming in ionized regions, how does that impact their star formation rate? And how does that depend, like whether a galaxy lives in an over or an underdense regions? So these are the kind of questions we have been asking, and yeah, how does the star formation histories look like? And so these questions basically have driven us to build this semi-numerical framework. So it's basically I call it a self-consistent model for galaxy evolution reionization. And the goal is to have a tool which is fast and flexible enough so we can scan a parameter space and we can test different physical models. And so basically where we start from is a dark matter only n-body simulation. And we extract the dark matter halos and build the merger trees or the dark matter halo mass assembly histories. But we also get from the simulation basically the density fields, so the distribution of dark matter. On the one hand, so we process the merger trees, which we feed into a simulated galaxy evolution model, which traces then sort of the buildup of the gas mass and the stellar mass throughout the history of a galaxy. And at the same time, we also feed the density fields together at each snapshot of this stellar mass, or we build basically our ionizing emissivity for each galaxy, depending on its history, and feed that ionizing emissivity distribution with the density feed into my semi-numerical reionization scheme, and we compute the ionized regions basically on the fly. And this allows us also at each time step to tell to give feedback into simulated galaxy evolution model, whether a galaxy already sits now in an ionized or still in a neutral region. So they basically, these two codes are fully coupled. That's fully consistent. So I just want to run you quickly through like which physical processes we include, and I think which also Rahul mentioned are key to do. So what we do is, we roughly assume that gas follows in the beginning sort of the dark matter mass. And so we have a galaxy will have initially gas, it will accrete gas, and a certain fraction of the gas is assumed to form stars. And then obviously the most massive stars will explode as supernovae and will eject a certain fraction of gas. And I think this is also very well known that then the low mass end or the faint end of your luminosity function, for instance, is basically then shallower or is suppressed. So, but your stars won't only like explode, they will also emit ionizing photons, which will start build up ionized regions, and you will get ionized regions. So, but if your galaxy, for instance, sits in the vicinity where you have maybe a large galaxy which has ionized that region, so what is happening to the galaxy? So the idea is that the gas is basically immediately photoheated by reionization. And so if you heat the gas, what happens is that then also the gas pressure increases. And however, if the gas pressure increases, the density of the gas only adjusts over the dynamical time scale to this increased gas pressure. And so it will take some time until in the end, you can imagine it's sort of the Jeans mass of galaxy formation has adjusted itself to the new temperature. So if you're raising basically by reionization, by ionizing the region, the temperature, that increases basically your Jeans mass of galaxy formation, but this increase only happens like over a dynamical time scale. All right, so what happens then if, for instance, your Jeans mass of galaxy formation is higher than the gas that currently your galaxy contains, then it will lead to a photoevaporation of the gas, or vice versa. If you want to accrete gas, but you will reduce the accretion because you're limited basically by this Jeans mass. So in a way, we implement this, that the Jeans mass of this galaxy formation is basically an upper threshold. This is how we take account for radiative feedback from reionization. So the key point here is really to take away is that radiative feedback from reionization increases over time as the gas within the galaxies have more time to adjust its density to the increased IGM temperature. So in Astraeus, we have implemented different radiative feedback models. So one is really what we call the delayed feedback. This is exactly what I have described. But we have also the option to explore a very extreme case, saying like, okay, the feedback is immediately happening. So that's a way to check like what would be the most extreme case. There's also various options of exploring different escape fraction of ionizing photons model, the default sort of a constant one. Then you can decrease, increase it with halo mass as you would like. Or we have also explored scenarios where it skates basically with the ejected gas fraction, which is sort of motivated by what radiative hydrodynamical simulations have found. And going further with the star formation rate is like, what I'm showing here is the average star formation rate history of a halo. And depending on when its environment got reionized. So for instance, for different halo masses, so we have the leftmost panel is for low halo masses, and then towards right, the halo masses increases. And the top row is basically if we include no radiative feedback and from reionization, and the bottom row is if we include radiative feedback from reionization. And as you can see, the radiative feedback from reionization affects the low mass halos below 10 to the 9.5 solar masses in halo mass. And the second key thing to notice here is that the earlier something got, the environment of the galaxy got reionized, the stronger is basically the star formation rate at the given redshift suppressed. So, I mean, you can see if you compare basically the colors at a fixed redshift here across different redshifts of reionization. You can see here the color changes, while here it more or less stays constant. So the earlier you're getting reionized, the stronger is basically the suppression of your star formation rate. And now you can imagine, because reionization is not homogeneous, but patchy, and in our case, it proceeds in an inside-out nature. So overdense regions are ionized before underdense region. What we will find that in overdense region, it's earlier reionized, so we have a stronger suppression of the star formation rate. And that's exactly what we're finding. So what I'm plotting here is, you can see the probability density distribution of the star formation rate, or here it's actually the ionizing emissivity, but which is very much proportional to the star formation rate. This is the case of no radiative feedback as a function of the overdensity, or the density of the environment, smoothed over a 2 megaparsec scale as a function of halo mass. And you can see, okay, the bulk of the ionizing emissivity will come like from intermediate mass galaxies, roughly around 10 to the 10. But the key thing I want you to notice is that if we look at the overdense low mass regime, then we can see as we switch on radiative feedback, I see that decreases the ionizing emissivity, which is in line what we have seen before. So in overdense region, low mass halos, their star formation rates will be more suppressed. So going further, we had a look more on the star formation histories. And this has been work which has been done by Laurent Legrand. He's a PhD student at the Kapteyn Institute. And he has looked at like, okay, how can we quantify, or how can we describe star formation histories that we have simulated, and how do they depend on the feedback mechanisms, and what do we find? And so what he has done is, so what you can see, he has plotted here a merger tree of a very massive galaxy, but I think it very nicely shows the sizes. So the sizes of the circles basically represent the halo mass, and the color code is basically star formation rate. And if you look, for instance, at the small circles, which are the low mass galaxies, you can see there are like black patches, which basically show you there is no star formation rate. We have episodes of no star formation. While if you look at the larger circles, with the more massive galaxies, you can see they have a smoothly continually rising star formation rate. And so if you plot this like quantitatively, here on the left side is basically an example. You can see, okay, that's a typical evolution of a galaxy. You have sort of, in the first case, you have sort of stochastic star formation. Because you have these galaxies are subject to supernova or radiative feedback from reionization, they basically have the episode which we have here identified as the black circles of no star formation. So they're really stochastic. And at some stage, they overcome basically this radiative feedback, the supernova and radiative feedback. So the feedback process can't completely stop star formation anymore, and it becomes more steady. So what we have done, or what he has done, is he has quantified like which stellar mass has been building up in stochastic regime, and what are the parameters that describe basically a steady star formation history once a galaxy becomes steady star forming. And here basically you can see the result for the stochastically or the stellar mass formed in the stochastic regime, as we call it, where star formation is stochastic. And I mean, the keynote is what you see here is basically as a function of stellar mass versus redshift. And as you can imagine, like if you go towards lower stellar masses, you are in shallower potentials, so you're far more subjective to feedback, and you have more of your stellar mass is assembled in the stochastic regime. And similarly, because your gravitational potential for the same halo mass as you go to higher redshifts become deeper, you are less affected by these feedback mechanisms. So it takes a shorter time to reach the steady star forming regime. And this is why you see then suddenly this decrease in the stochastic mass fraction. And obviously, if you enhance the radiative feedback, then this will raise the stellar mass assembled in the stochastic regime. So that's basically the impact then of radiative feedback. And so what we also have checked, Laurent has derived then for the steady star forming regime basically fits to the star formation histories. And this is basically the fitting function. So it's an exponential growing one. And so to check whether this is correct, we have plotted basically the stellar mass to UV light ratios. And so the actual result from Astraeus is the blue dashed line, while our fit results is the solid blue dashed line. And they're in the regime where we are reliable, sort of really can predict galaxies, because they're in the steady star forming regime. They actually match quite well. So, and that brings me actually to the quick summary of basically what currently from Astraeus is out there. So these are currently the 4 published papers. So with Astraeus 1 describing the model and radiative feedback models, Astraeus 2 looks at cosmic variance and environment of LBGs. Astraeus 3 is the environmental dependence of ionizing emissivity in the escape fraction and the question which galaxy reionizes the universe. Astraeus 4 is basically what I have just explained in the last 2 slides. And we have forthcoming also, we have included now metals and also the dust enrichment. We're working on Lyman-alpha emission and black holes and IGM. And I believe I'm out of time, and I leave you with my conclusions. Thank you.
Thank you for your talk, Anne. I think that's really all your time, including the time for questions. So I encourage everyone who has questions, drop them off in Slack. I think there are already one, now two, so please get to them afterwards. Let's move on to our next talk from Aaron Smith. Aaron, are you with us?
Yes, let me just.
Yes, I see you now. Great.
All right, how does that look?
Looks perfect, and you sound loud and clear. Take it away.
All right. Let's get rid of the boxes there. All right. So yeah, thanks to the organizers for this mini conference here. And I think there's a lot of really good science still, of course, to come with just the beginning of the talks happened. So today I'll talk a bit about the Thiessen simulations and in particular some Lyman-alpha applications here. So I have listed some of the people involved with this collaboration, but also there are a number of other projects that are related, and I'll advertise maybe one or two of these as well. So Thiessen is the Etruscan goddess of light, and so I think the reasoning for this name is self-explanatory at this point. But they really shine for getting good statistics, meaning that the box volumes are large enough to get massive galaxies that contribute, especially at the end of reionization, where their star formation rate densities are extremely high. So we've already had quite a bit of introduction at this point. So I mostly want to emphasize that there are definitely a number of open questions that remain in this process. Although many of these have been addressed over the past decades, and we sort of understand the rough picture. There are quite a few details, and what we hope to achieve with Thiessen is to connect in this space, this niche of the large volume, to also connect with the galaxy properties, which are of course responsible for reionization of the sources. So there were 3 papers that were out about a month ago on this by Rahul, Kannan, Enrico Giraldi, and myself. And so, yeah, let's jump in a bit to some of these results here. So as mentioned, this combines essentially the Repo-RT radiation-hydrodynamics solver with the illustrious TNG galaxy formation model. This has all the ingredients as best as we can in this framework. In order to go beyond this, of course, we need to swap out some of the ingredients for more accurate ones in the future. But this is also kind of a nice regime where we're computationally accessible to do this at this point. So as was mentioned, we have a number of these kind of advantages in terms of adequate resolution, but also looking at other types of physics, the convergence and halo mass dependent escape fractions and alternative dark matter as well. So on the right, of course, this is a proto cluster environment that's formed by the end of the simulation. So this is a movie of the bubbles forming, and on the top you can see the neutral fraction history, and the bottom you can see the photon density. As these really do complement each other. As you can see with the blue regions, you're starting to be able to peer into the volume and see the imprint of the large scale structure. And in the right, you see these bright regions. And if you look closely in detail, these movies are available online at the Thiessen-project.com. you can sort of see how these sources start flickering and contributing as well. So I'll spend the rest of the talk mostly discussing Lyman-alpha as a probe of reionization, which is, of course, one of the signposts that we have for galaxies to properly assess their redshift measurements or distances, and also to characterize what kind of star formation activity and so forth is happening here. But I will emphasize, you can really see this is the evolution of the same sub-region. It's a slice that's 90 megaparsec across. And you can really see as the ionization, the global ionization fraction changes, this is the Lyman-alpha emission, which represents the resolved recombination, collisional excitation emission, and then also the unresolved sources, which in the context of this model represents the birth clouds for star particles. And these contribute roughly at the level where the escape fraction from birth clouds is 37%. And so naturally you recover that remaining emission in these other channels. So of course, Lyman-alpha is a complex line, so I won't address everything here in this talk. I'll mostly focus on the IGM, which is what this simulation can answer best. But look forward to Thibault's talk and others as well. So in that context, just to put this out there, we can reconstruct luminosity functions as a function of the UV magnitude. And as was mentioned before, we really do have these bright galaxies which are significantly dust attenuated in order to match the observations here. So in the context of this model, essentially what this means is that this is driven by the star formation, and then this directly translates to the Lyman-alpha luminosity function, where this has some slight modulations because of the recombination and collisional excitation sort of redistributes where that intrinsic emission lies. And this, of course, is not observable. To move to the observations, you need to account for galactic scale and even ISM scale radiative transfer effects, which I'll discuss a bit later. But I do want to point out that we have these nice catalogs of all these properties for every galaxy. So, for example, you can look at the stellar mass of a halo and see what the Lyman-alpha luminosity is for that. And there's, of course, a larger spread at low masses where things are more stochastic, as was mentioned. But in this high mass range, there's a very tight relation. So kind of moving down here, we can sort of estimate sort of the fraction that is represented by this local H2 region contribution. And it's higher for these higher star forming regions. So it kind of also gives an impression of the limitations of this model, which is mostly lies in the unobservable range. So, but I will point out as well that if you take the center of luminosity position for each halo and then subtract the center of mass, this can actually be offset by quite a bit. And there's a bias towards the highest star formation rate galaxies to be more offset from where the mass is, from where the starbursts are happening. and similarly with the velocity center of luminosity. And there's another effect which is important for to impact line profiles, is that the halo like velocity dispersion is actually going to be larger than the luminosity dispersion. Now this is what this represents, the lines that go in. Of course, these lines will also be resonantly broadened as well by the radiative transfer process. So briefly, results are as expected. We're able to cast rays around galaxies for 45,000 galaxies in the simulation. And the blue side is significantly suppressed, while the red side has large transmission at lower redshifts when reionization is, of course, further progressed, and then low transmission at very high redshifts. But you can see, if you look in particular bands, this is roughly where we would expect the red peak to occur. Then this nicely, this sort of signals that Lyman-alpha emitters, if you can properly characterize them, do probe reionization quite well. So yeah, briefly, there's also some mass dependence and brightness dependence, as this affects the local ionized bubbles, but it also represents the imprint of the velocity structures around these galaxies. For example, the protoclusters have large webs of filaments, which impacts the visibility. So even at low redshifts, in this context, redshift 6, you have an imprint on the brightest galaxies having actually lower transmission in certain bands. But then as you go to the red, of course, this is offset because you escape this local bias here. So just to highlight what's actually going on here is these images show at 200 kilometers per second, around roughly where the peak cuts off. You have a very dense covering fraction of this octopus-like morphologies around these galaxies. And in fact, if you go to less massive galaxies, so this column is redshift 6 and then 7, and then we choose a mass and then go down a factor of 10 each row. If you go to less massive galaxies, you still have some imprint of the cosmic structure, which is inevitable, but this actually, on average, in this well-reionized region, the median is quite high, so almost unity transmission compared to the average on the left here. And so this imprints on the covering fractions. So at 200 kilometers per second, there's a clear change here in increased coverings for more massive galaxies, which is actually taken away when you go to, say, 400 kilometers per second. So briefly, I guess the point of this is, how can we really move past this intrinsic to the observed? And there's some modeling. I'm running low on time, so I think I'll just jump to the punchline, is that the main drawback for Thiessen is this effective equation of state sub-resolution treatment of the ISM. And there's really no way for us to get a good handle on whether this red peak enhancement is imprinted on the H2 region local scales or on the CGM scales from these simulations. Of course, we can go to zooms and see how things are changed, and see some imprints of observable red peaks, even without this IGM cutoff. And then briefly just mention that there are IGM galaxy connections in Enrico's paper. And then I have a student doing escape fractions of ionizing photons, and you get these imprints of these disks in these more massive systems. But the takeaway here is that actually the global escape fraction goes down as it transitions to being dominated in the emission by the most massive galaxies, which is above 10 to the 10 here. So with that, I'll just leave my summary, which is that there's a lot of data products that will be publicly available, and also you can go to this website for more information. And much of my analysis is done with this code as a plug. So thank you.
Thank you for your talk, Aaron, and you use up all your 15 minutes. So we don't encourage that, but that's your choice. This is fine too. So everyone, please drop your question in the Slack channel as well. And I think Aaron will get to them afterwards. So this is time. Let's move on to our next talk from Daniel Ceverino.
Aaron, can you hear me?
I can hear you loud and clear.
Perfect. So let me share Okay, I hope you can see. Can you see the slides?
Yes, I can see the slides.
The cursor.
And your cursor as well. Perfect.
Okay. So first, I would like to thank the organizers for this opportunity to present my work here about the FirstLight Simulations. This is a list of my collaborators. I would like to highlight Michaela Hirschman. So in this project, we were coupling her models of light emissions into the FirstLight simulations. So this is the questions that we are trying to answer in this project. Is about the galaxy diversity. So if we have a high redshift given galaxy set of observations, we can always ask this question: how can we know if a given galaxy set is representative on the underlying populations? There are always going to be some kind of observational bias that we need to take into account when we study galaxies. In particular, we're going to focus here the second questions about the emission lines in the rest frame optical, oxygen 3, 5,000 angstrom versus H alpha. So is the oxygen 3 brighter than H alpha in all the first galaxies? And this is something that we can now start to answer using simulations. This is the slide for the FirstLight simulation. This is a large sample of 300 zooming cosmological simulations of the formation of the first galaxies. So the key strength of these simulations is that this is a complete mass selected sample. So within a given cosmological volume, I'm selecting all the halos with a given mass range between a few times 10 to the 9 and a few times 10 to the 11 solar masses, redshift 5. And then we simulate all of them with very good resolution. We have a dark matter particle mass of 10 to the 4 solar masses, only 10 to the 4 solar masses. You can imagine that we are dealing with galaxies that are really well resolved. We can resolve the multi-phase ISM with a very good resolution. So this is the largest database of zooming simulation with this kind of resolution. Other than with the ART code. So let me show you some first results. We found in general very good agreement with observations. This is the stellar mass versus the virial mass, redshift 6 and redshift 10 basically. So the points are this FirstLight test, and the areas are the result from abundance matching. So this is a more up-to-date plot, the stellar mass again versus the virial mass, redshift 6. These are now including more massive galaxies, so we can extend to higher stellar masses. So we are consistent with the observations by Stefanon et al. Once we correct by the difference in IMF and the difference in cosmology. And also on the right, we see the star formation rate versus the stellar mass. We are in agreement with the observations by Salmon et al. At redshift 6. So we are resolving the main sequence. And now, including more massive galaxies, you can see we can have some example of galaxies with a 10 to the 10 solar masses that forming stars at the rate would be 100 solar masses per year, redshift 6. So these are some results, and these galaxies are all bursty. If we now plot the specific star formation rate as a function of time, these galaxies spend 70% of their time in bursts of star formation. So in a previous paper, we select the properties of, we study the properties of like 1,000 bursts of star formation. That's basically this burst here. So we study the typical duration of the burst and the typical height of these peaks in this paper here. But now let's focus on the diversity of galaxies at cosmic dawn. So what we're putting here is the stellar mass versus the UV absolute magnitude. Again, we are consistent with observation based on et al., but we can extend the observed range to much fainter and smaller galaxies. But we focus on a fixed UV luminosity. We can see that the SED of these galaxies are very different. We focus on one galaxy that has very low stellar mass. That you see this galaxy is dominated by a very bright young population with very steep UV slope. But then another galaxy with the same UV luminosity, but now is mostly populated by a slightly older population with a flatter UV slope. So this is what I'm talking about diversity. So now we are going to concentrate on the observation or the smoke observations. We are selecting galaxies with a fixed UV luminosity at redshift 6, like minus 19, something that will definitely be able to observe with James Webb. So we are now focusing only on these galaxies. We are getting rid of all these scaling relations. So let's take a look at these galaxies. There's a few examples that are ordered by the specific star formation rate. So a galaxy here on the left is now undergoing a burst of star formation. It's at the peak of the burst due to a massive merger that brings a lot of gas to the center. So you see the center is very dense and compact. This would be typical starburst galaxy in that sense. A more typical star formation red galaxy, now leaving the main sequence at the redshift, is now in the middle. You can see now the galaxy, the gas is distributing a extended region. The clumps are now much smaller in size compared with the previous case. We can see even examples of galaxies below the main sequence. These are the ones on the right. Now here the gas distribution is much more extended, much more smooth. There are no clumps here in this kind of galaxies, with the specific star formation rate is much lower than the main sequence. So we see large diversity of properties, and now we can concentrate on the emission lines, in particular the emission line of the Yuxiang Qin line, 5,000 angstrom. So this is the Gibelin width as a function of the specific star formation rate. So we see a factor of like 10 variation, 1 variation in the Gibelin width, which is an example below 100 solar masses, and some extreme cases like 1,000 angstrom for these galaxies with the burst of star formation, very high specific star formation rate. But also we can see that there is some scatter in this relation, especially we focus on galaxies on the main sequence. These are these galaxies here in the middle. We see some scatter. So the scatter is mostly driven by the ionization parameter. We are using the models by Michaela Hirschman et al. So this now the ionization parameter is not constant. It's driven by the different star formation rates in the galaxies. So galaxies with very high ionization parameter have a boost in Yuxiang Qin that we see this galaxy here in blue. So now we can take the ratio of Yuxiang Qin and H alpha and study the different population that we can see here as a function of the specific star formation rate. For example, we focus on these blue points. These are the galaxies with higher than average ionization parameter. This is what we call Yuxiang Qin bright galaxies. For these galaxies, Yuxiang Qin is brighter than H alpha. But this is only 20% of the galaxies on the main sequence. The majority of the galaxy are actually H alpha bright. H alpha is brighter than the Yuxiang Qin. So now we are trying to see if there is any kind of global property that is also correlated with this Yuxiang H alpha ratio. And for that, we need to take a look at the maps in these emission lines. Putting here at the top, one galaxy that is H alpha bright. You see the H alpha map, the Yuxiang Qin map, and also the map of the ionization parameter. So this galaxy is very extended. The oxygen 3 is mostly concentrated in those large clumps that are extended over the galaxy. But if we now compare with a galaxy, there is oxygen 3 bright. So now this galaxy, the oxygen 3 is brighter than H alpha. But you can see that the galaxy, the star-forming regions are mostly concentrated in a compact center. So the center is very dense, has very high ionization parameter, and that's why the oxygen 3 is boosted. So all these compact-like objects are going to be oxygen 3 bright galaxies. If now we can look at the size of these regions, so this is, for example, the size, the effective radius in H alpha on the left, and the effective radius of oxygen 3 on the right. So we focus on these blue points here. These are the oxygen 3 bright galaxies that are always very compact. So if we have a population of observed a sample of galaxies that is oxygen 3 bright galaxies, we are going to infer very compact objects. We need to also take into account the more extended objects that are mostly H alpha bright. That would be this galaxy here. They are all small in general, but this a significant scatter in the relation depending on the properties of the galaxies. So this is my summary. So these FirstLight simulations follow the formation of the first galaxies during cosmic dawn. We found a factor of 10 variation in the equivalent width of the oxygen 3 line, mostly driven by factor 40 variation in the specific star formation rate. And also variation in the ionization parameter drive a dispersion in the equivalent width and also in the H3 H alpha line ratio. Even for a fixed specific star formation rate, this is true even for galaxies at the main sequence. These oxygen 3 bright galaxies or emitters are more compact or clumpy than with higher ionization parameter than H alpha bright galaxies. And finally, this alpha emission is significantly larger than the oxygen 3 emission. So, thanks.
Thank you for the talk, Daniel. So,
on time.
what's the questions? Let's see. Looking at the Slack. So far, no one has questions. So, Maxime, go ahead and ask your live question.
Yeah, thanks. So thanks, Daniel, for the talk. I'm just wondering, on your last point here, do you have any feeling for what drives this difference in extent? Like, how do you explain that the H alpha, I mean, in the end, it's the same stars that are going to create the ionized gas, right?
Yes, but these are different conditions for H alpha and oxygen 3. Oxygen 3 is boosted compared to H alpha in regions which are very dense with very high star formation.
Okay, so it's just a difference in the morphology of the star forming gas.
So this is what you see here. You see that the outer regions have lower ionization parameter. That's why the oxygen 3 is lower compared to H alpha.
Okay, thanks.
Welcome.
Let's take the next question from Ryan. I see your raised hand.
Hi, Daniel. Nice talk. I was curious about this number of, I think you said about 20% of the main sequence galaxies had O3 brighter than H alpha. The rest optical observations of redshift 2 to 3 show at least, something like half of the galaxies have O3 brighter than H alpha on the main sequence at, sort of 10 to the 10 solar masses. So I was wondering what changes between, say, redshift 2 and 3 and the higher redshifts. Are you finding much lower metallicities, which is why the O3 is dropping relative to H alpha? Because I would naively expect that the O3 versus the Balmer lines is actually going to get a little stronger as we go to higher redshifts.
Yeah, but the metallicity gives you much lower than expected oxygen 3 compared to H alpha. The metallicity of these galaxies is really low. So we are really in the regime of in which the regime in which if we increase the metallicity, we increase the oxygen 3 H alpha.
Got it. Thank you.
Yeah.
Right, we have a question from Slack from Laura Vigo. Do you have C2 emission in your simulated galaxies? Would be interesting to see if C plus O3 ratios as well.
Yes, that's something that in progress. We are also getting the models from C2. Yeah. Really soon.
Great. There's another one from Slack, from Tom Bax. Do you have any indications of what drives the compact star-forming regions in the O3 dominant galaxies? Is this due to mergers among main sequence galaxies?
Yes, on mergers.
Oh, sorry.
Let me see. So yes, mergers can give you these compact regions, but any kind of for example, violent instabilities can also drive a lot of cold gas to the center. So any kind of compaction event, even driven by a merger, can be also driven by instabilities. If drive a lot of gas to the center, give you this compact, dense cores.
Thank you. I think that's all the questions we have now. So if for any further questions, go drop them in Slack. I think that concludes our first section of our two-day conference series. So get a coffee, go use the bathroom, and come back in 15 minutes. And we'll start talking about galaxy formation in the context of EOR. speakers for the next section, if you want to quickly try out your slides, you can feel free to do that. I'll be here to help you out, in case any difficulties. And if you're playing videos, it's important to try to make sure it plays. We had a glitch earlier.
Is it all right if I give it a go right now?
Yes. Are you speaking at the next section? Let me check.
Yeah. Number
Go
2.
ahead. Give it a try.
Can you see that?
Yes.
Okay. And the slide change as well?
Yes, correct. Yeah, it works. Great. Perfect.
Hi, Aaron. Do you want me to test the slides?
Yeah, please do. Welcome back. You're up next, I think.
Yeah.
Great.
So if I share this, do you get the right slides?
Yes.
And it works.
Yes.
Okay, perfect.
just a final shout out to any of the other speakers if they want to test their slides or test their audio. Okay, we've got about a minute to go until the start, so just hope everybody's starting to drip back in. So we're going to start session 2, which, let me remind the name that we've given this one, Model Galaxies in the Context of the Epoch of Reionization. So first talk up is Maxime Trebitsch from Kapteyn. Maxime, if you could bring up your slides, please.
Yeah, does that work?
Works great, yeah. So when you're ready, take it away.
Okay, so maybe I'll start now. So thanks a lot for the opportunity to talk today. And indeed, I've moved. I'm now at the Kapteyn Institute in Groningen. And today I'm going to talk about the Obelisk simulation, which is a project that I've been leading in collaboration with this group of people here, some of which are in the room today. So the main thing that I'm interested in with this simulation is to study which are the sources of reionization. And we've already discussed that a bit today, and I'm not going to introduce it too much. But broadly speaking, we usually think of the source of ionization as either stars or massive stars in galaxies or quasars. And traditionally, people find out that quasars are not numerous enough to reionize the universe when you compare the number density or the ionizing emissivity of bright quasars at high redshift to the UV background that you estimate. Note that this is still very highly debated, even for the bright end of the quasar luminosity function. There was a paper just this morning on arXiv by Andrea Gratian and collaborators suggesting that the bright quasars might contribute more than expected. But in most studies, people focus mostly on the galaxies because you have enough galaxies if you assume that enough radiation goes out of them to reionize the universe and be consistent with observational constraints and the reionization history that we have. But going back to AGNs and to very faint quasars in a way, there's been more and more studies looking at the faint end of the quasar luminosity function. I'm showing here a compilation by Guochao et al. From a few years ago, showing the number density of AGNs as a function of the luminosity. And when you go to the faint end of this AGN luminosity function, you might have more AGN than expected. And if these AGN are all contributing significantly ionizing radiation to the UV background, you might end up, when you convert that to an actual measurement of the UV background, you might end up with a contribution of AGN to the UV background that's very high at high redshift, up to more than 30% at redshift 5.5 or 6. There are lots of assumptions going into this, and I'm not going to discuss all the discussion that exists around these measurements. But the fact is that it's interesting and worthy to study whether AGN are relevant or not for reionization. But one difficulty that we have in this is that even if you look at the faint end of the AGN luminosity function, the number densities that you have is typically 10 to the minus 6 Lyman-alpha megaparsec. And what that means is that effectively, if you want to have several faint AGN in your simulation volume, at least in this luminosity regime at redshift 6, you typically need to have a simulation volume that's of the order of 100 megaparsec on a side. And if you want to study how radiation escapes from this AGN to test whether they can contribute significantly, ionizing radiation or not, you need to also have a very high resolution. And that's very challenging, as Rahul mentioned in the review talk. So what you can do is, instead of having a large volume, you can decide to take a large volume where you would expect some of these bright AGN, well, not so bright AGNs, and you will focus all the computational power on this specific environment, doing some form of zoom simulation, but instead of zooming on one halo, you would zoom on an environment. And this is what we've been doing with the Obelisk simulation. And so we call this simulation Obelisk, first of all, because it focuses on an overdense region, but also because the obelisks are effectively rays of light cast into stone. So that is fitting for a reionization simulation, I think. So giving a few details about the simulation, because in the end, this is the numerical simulation SIP. This is a zoom on an overdensity in the horizon AGN simulation that we've run down to redshift 3.5 or so with a variable speed of light approximation. And we have a very high resolution in the ISM. I'm going to show a picture that's more relevant for the galaxies here. So we have a high resolution in the ISM, and we've decided to take the approach of calibrating the models on small scale simulations for the stellar physics, for instance, where we use a turbulent model for star formation and this mechanical supernova feedback that takes into account the terminal momentum from supernova feedback. We also have a fairly evolved black hole physics model that includes some fairly standard Eddington-limited Bondi accretion, dual mode for the AGN feedback, and more importantly for this talk, we're following the radiation produced by the black holes as a function of the black hole properties. And we try separately the two sources of radiation that are stars and AGN in the simulation. In terms of high resolution, this is typically a view of the large scale environment of the most massive galaxy at redshift 3.7. And we do have a good description of the large-scale environment, but we also start to have a really good view of what's happening inside these galaxies. And comparing to the previous generation of simulations, like for instance, Horizon IGM, from which the simulation was zoomed in a way, or Eagle or Illustris or whatever you prefer, this is the type of improvement that we get in resolution. So not only we get more details in the filaments, but we get much more detail in the galaxies in Obelisk. And importantly, we do get a fairly reasonable resolution in the circumgalactic medium as well. Okay, moving on to some results. The first thing that we've done with the simulation is just to look at what's the history of this environment. And doing that, we've been measuring the cosmic star formation rate density as a function of redshift in the high resolution region that corresponds to this overdensity. And these are the two lines depending on whether we take only the central region or all of the high resolution region. And of course, it's very much above the average cosmic star formation rate density given by these green points. But when you compare that to data that we should actually compare with, which are these observations of high redshift protoclusters, it seems that the simulation is fairly well in line with this type of overdensities in the early universe. In more detail, when we look at the luminosity function per given redshift, so slicing this at redshift 6, and we look at the raw luminosity function in the UV, we get this black line, which again is significantly above the observational constraints taken, for instance, from Achimatech. But there are two reasons for that. One is, as I mentioned, that we have an overdensity, and when we actually compare with the data points that we found for overdense regions in the early universe, which are these two data points from Castellano et al., we see that these overdense regions are expected to have an increased UV luminosity function. And at the same time, when we take into account the dust that is present in the simulation and that we track as galaxies evolve, we can infer how much attenuation we get in the galaxies, and that's this red shaded area that really corresponds to a different prescription for the dust attenuation. And when we do all of this, it looks like the Obelisk simulation gives galaxy populations that are in reasonably good agreement with observations. Keeping in mind that there is no calibration directly there, it's just the subgrid models have been calibrated on higher resolution simulations. Now, in terms of black hole physics, because that's really something else that we track in the simulation, I'm showing here just the black hole mass of stellar mass in the simulation, and compared the data points from the simulation to the trends found by observation at lower redshift, that are these two lines. And there are two things in this figure. One is on the left here, the plateau kind of is purely due by the way we are seeding black holes around 3×10⁵ solar masses. And what we see is that until the galaxies reach a high enough mass, the black holes don't really grow, which is something that we completely expect. But when the black holes start to grow, they are growing with, when they're co-evolving with the galaxy in a way that is consistent with what we're expecting from the low redshift universe. Okay, moving on to the reionization history of this environment. I'm showing on the top here the really the reionization evolution of the high resolution region. We can see the small bubbles that are growing until around redshift 6 or so, when all of the high resolution region is fully reionized. And at the same time, we can see the UV background that starts to establish itself. A bit more quantitatively, we can actually measure directly the reionization history in the high resolution region, and that's this blue shaded area, and compare that to the expectations from observations in the real universe. And one thing that's interesting, I think, in the simulation is that on average, the reionization history of the Obelisk volume, which is overdense, seems to match broadly the observational constraints that we have for the average universe. And this is not something that we really expected, because you could argue that in overdense regions, you have more gas, so reionization should happen later. But at the same time, you could argue that because you have more galaxies in IGN, reionization would happen earlier. And it turns out the two seem to balance each other fairly well. I wasn't planning on talking about this, but Rahul said I should, so here it is. We also measure the reionization history of the Obelisk volume, but there is a big caveat here, which is that the typical volume that we have in the simulation is not big enough to really track the size of helium ionization bubbles. So this is not really expected to track any helium ionization history. However, we could use the simulation, and we will use the simulation to look at the helium ionization sources by measuring how much helium ionizing radiation escapes from galaxies in H. Anyway, going back to H1 reionization at higher redshift, because in the simulation we are following both stars and AGN, and the radiation from both, we can track which are contributing more to the UV background. And I'm showing on the left the emissivity, with the thicker lines being the escaped emissivity from AGN in green and galaxies in orange. And we can see that for all the epoch of reionization, it's really the galaxies that are dominating the ionizing emissivity, even though their escape fraction is on average much lower. Very preliminary, because I've just started this analysis, because last year has been challenging in terms of work. On the left, I'm showing here just at redshift 6, the ionizing escape fraction as a function of stellar mass for all the galaxies in the high resolution volume. And we can see that there is a huge scatter, but it seems that higher mass galaxies have significantly lower escape fraction than the lower mass galaxies. Because we track the dust in the simulation, we can do the same exercise by taking into account the dust attenuation, and it seems again that more massive galaxies have a significant dust attenuation, and to an extent that could be affecting the Lyman continuum escape fraction significantly. But really, this is mostly true for the most massive galaxies. So a bit more analysis needs to be done before checking how important this really is. And what that tells me is that I really need to finish the paper. And finally, when we put all of this together, we can go from the simulation to measure the total UV background and compare that to observations. And that's what I've done here with these three thick lines corresponding to the total UV background in blue, the galaxy contribution in orange, and the AGN in green. And at all relevant redshift for reionization, it's again galaxies that seem to be completely dominating the UV background, even in that environment that is fairly favorable to black hole growth. And I think I will leave you with some of my conclusions. Thank you very much.
Thanks very much, Maxime. Really nice talk. We have a couple of questions on the Slack, so I'll just read them out now. First one is from Daniel Ceverino. For AGN feedback, which mode, thermal or jet, is more important at these high redshifts?
So thanks for the question. Most reasonably, it's the, at least for most of the simulations, definitely the quasar mode. So this quasar wind modes that is dominating overwhelmingly, because the radio mode only comes into play in the simulation at low accretion rates, and you only get that for the most massive. Well, for the galaxy, it only makes a big difference for the galaxies when the black holes have grown enough, which happens at relatively later times.
Great, thanks. There's another question from Rohan Naidu. What is the duty cycle of Lyman continuum escape from AGN in your sims? In your galaxy sims, we see very bursty, stochastic escape. Are AGNs smoother? And he says, thinking about the disco UV background at Z5 to 6.
So this is a really good question, and I really need to do the analysis. But I'll get back to you as soon as I do that, I guess.
Time for one more question, if anyone wants to quickly ask one on Slack. Otherwise, I've got a very quick one. How much do you think your results depend on the actual protocluster descendant mass? So this is obviously just one individual protocluster. Do you see there being some variation for higher mass objects?
I mean, I would expect that higher mass, you might have some, maybe a bit more importance of the AGN, but you would need to go to like in the actual region dominated by very bright quasars. I do expect some difference, but I don't think that this is numerous enough to have a huge effect on the global reionization. If that answers your question.
Yeah, that's great. Thanks. So yeah, if anybody's got any further questions, please put them into Slack. But we will move on now to Harley Katz from Oxford. So you can just bring up your slides. Oops.
Can you hear me now?
I can hear you, yeah.
Okay, very good.
See your slides yet? Hopefully, yeah. Okay.
Yeah, there.
Yeah. I'll give you a quick 1-minute warning when you've got a minute left before the questions. But yeah, when you're ready, take it away.
Sounds good. Thank you. So thanks so much to the organizers for giving me this opportunity. I'm Harley. I'm based at the University of Oxford. I primarily work on cosmological radiation-hydrodynamical simulations and magneto-hydrodynamical simulations of galaxy formation during the Epoch of Reionization. And over the next 10 to 12 minutes or so, I'll tell you a bit more about the first results from Sphinx 20, which is the next generation simulation as part of the Sphinx group. So if we want to understand how galaxy formation differed, for example, in the early universe compared to in the local universe, we need some sort of observational probe of the interstellar medium at high redshift. I would argue that currently ALMA is probably our best facility. Of course, James Webb is launching soon. Nevertheless, since ALMA is what we have today, infrared emission lines are probably our best tracer of the high redshift interstellar medium. Here's just an example from one of Nicholas Laporte's recent papers where the different color contours, the red, the green, and the blue, show you the emission from dust, oxygen-3, and carbon-2. Now, I think the biggest question is how do we then translate the emission line luminosities and distributions that we see at high redshift into actual galaxy properties? There's a number of ways of doing that. Here, I'm just showing you a particular example from our 2019 paper, where you're looking at phase space diagrams of density on the x-axis versus temperature on the y-axis, and each of the individual panels shows you a different infrared emission line. If you focus, for example, here in the top left and top center panel, you can see the carbon-2 158 micron line is very, very bright at very high densities and very low temperatures. In contrast, the O3 88 micron line tends to be more bright in ionized gas, higher temperatures. It's probably photoionized or heated by supernova feedback. And the game we'd like to play is essentially how do we combine the different lines that we could potentially observe with ALMA that probe different phases of the ISM into individual galaxy properties. Now, unfortunately, bright lines such as carbon-2 and oxygen-3 that we have many observations of at high redshift, they're impacted by a huge amount of physics. So I've just tried to come up with a particularly non-exhaustive list such as ionization parameter, escape fraction, photodissociation region covering fractions. Things like ISM density, metallicity, CMB attenuation, all of these things affect the emission line luminosities that we see. To show you this a bit more quantitatively, on the left-hand side, I'm showing you two plots where on the x-axis, we plot the oxygen-3 to carbon-2 luminosity versus, for example, the ionization parameter. Don't worry about the different line styles. The different colors represent different redshifts. And what you can see is that as the oxygen-3 to carbon-2 luminosity increases, so does the ionization parameter. Similarly, if you look at the bottom panel, we just replace ionization parameter with F-escape. You can see that there's a very strong trend that galaxies with high oxygen-3 to carbon-2 luminosities have very large Lyman continuum leakage. So the trick we need to understand these lines is figuring out how to break all of the degeneracies between each individual parameter. Now, I would say at high redshift, things become even more complex because the galaxies are seemingly different. This is some recent work by Harakane et al., where they looked at the star formation rate versus the favorite ratio of oxygen-3 to carbon-2 luminosity. You can see the high redshift galaxies between redshift 6 and 9 are showed by the red points, and they fall significantly higher than the low metallicity dwarf galaxies we have in the local universe, similarly to the local starburst galaxies. If they looked at the carbon-2 luminosity versus the star formation rate directly, they also found that there's a significant number of galaxies that have significant carbon-2 deficits. So there seems to be some difference between the low redshift galaxy population and the high redshift universe that we're going to have to explain if we're going to be using these two lines to extract galaxy properties. Now, numerical simulations, I think, are some of the best tools we have for actually understanding what's going on during these epochs. And I think Sphinx 20 is particularly strong to understand these two emission lines. So Sphinx 20, as I mentioned, it's the next generation Sphinx simulation. It's a 20 megaparsec box, and we average around 20,000 galaxies per snapshot between redshift 10 and redshift 4.68, which is the final redshift of the simulation. The spatial resolution is about 10 parsecs at redshift 6. It's a little bit higher at high redshift. So we don't completely resolve the interstellar medium, but we do a pretty good job at getting this multi-phase structure. I would say most importantly for this simulation, though, is that it includes on-the-fly radiation transfer and non-equilibrium chemistry. And the reason why that's important is because when we model the carbon-2 and oxygen-3 emission from these galaxies, what we do is we post-process each individual gas cell in the simulation with a cloudy model. And then we build up the emission line maps sort of cell by cell. And essentially that's around like hundreds of millions, if not billions of cloudy models that we do. So what you can see in these maps is the left-hand side is the neutral hydrogen column density. The center panel shows you the carbon-2 surface brightness map, and the right panel shows you the oxygen-3 surface brightness map. And you can try to sort of like pick out individual regions here and see what's going on. But each individual cell, like I said, is very sensitive. It has a temperature, density, metallicity, and radiation field that's all captured on the fly. So you can really see the complexity that goes into this. So one of the first things we found out when we ran these models is that if we make what I call naive assumptions, and by that I mean if we assume that high redshift galaxies have solar abundance patterns in terms of their metallicity abundances, as well as something like a stellar IMF that's consistent with Krupa, we find that the simulations lead to results that are incompatible with observations. To show you this a bit more in detail, the x-axis on the left plot is star formation rate, and I'm showing the oxygen-3 to carbon-2 luminosity. The high redshift galaxies are once again shown in red and black here in the top right of the plot. And you can see with these naive assumptions, the simulations fall almost an order of magnitude short of what we see at high redshift. In contrast, if you look at the carbon-2 versus star formation relation, you can see that the simulations with the naive assumptions actually do a pretty good job at matching what we see at high redshift. Finally, if you look at oxygen-3 by itself versus SFR, once again, we're in a regime where the simulations are almost an order of magnitude below what we find at high redshift. So the question we asked is, how can we reconcile this disagreement? So we came up with two ideas of how we could do this. The first one was, can we relax the idea of solar abundance patterns to, for example, going to non-solar abundance ratios, which may lead to something like higher oxygen to carbon abundances. If you do something like this, you will end up in a situation where you'll increase the oxygen-3 88 micron luminosity, but you'll decrease the carbon-2 158 micron luminosity. Now, this might help you a little bit, but the problem here is we saw good agreement between the carbon-2 luminosity and the star formation rate. So if you go this route by itself, you might actually cause a further disagreement with observations. However, we also propose potentially increasing the metallicity of the galaxy by, for example, assuming a more top-heavy initial mass function than Krupa. And in this case, if you just overall enhance the metallicity of the galaxy, you'll increase both the oxygen-3 88 micron luminosity as well as the carbon-2. And the hope is that these two effects, which go in opposite ways for carbon-2, they'll balance each other out. But since we underproduce oxygen-3, the two effects go in the same direction, which should push us hopefully more towards the observations. Now, of course, that all seems very ad hoc, and you can ask yourself whether or not there's precedent for these changes, and I would argue that there is. What you can see here on the left-hand side is a plot from Roberto Maiolino, where he showed, for example, the enrichment of individual metals as a function of time since stars formed in the galaxy. The red line represents oxygen, and you can see that it peaks very early on after star formation, and that's because oxygen is primarily enriched in a galaxy via type 2 core collapse supernova. In contrast, if you look at the black line, which represents carbon, you can see that there's a much longer timescale for carbon enrichment. That's because you can also get carbon from AGB winds as well as type 1a supernova. So a high redshift galaxy, which is obviously going to be very early on in the universe, might sit more towards the left-hand side of this plot, which would indicate that instead of using solar abundance patterns, perhaps we should consider something like core collapse supernova. In the context of the initial mass function, this is just some work by Chon et al. In 2021, where they looked at the IMF that formed in simulations at different metallicities. So the x-axis represents the mass in the stars, and the y-axis represents the cumulative amount of mass that formed in stars less massive. So the Chabry IMF, which is typical, I guess, for a low redshift universe, is shown as this dashed black line. And you can see that the simulations that have metallicity of 1/10 of solar, shown by this yellow line, more or less reproduce what you'd expect for a Chabry IMF. However, if you go to lower metallicities, for example, 10 to the minus 2 solar, all the way down to 1 millionth of solar, you can see that the IMF becomes significantly more top heavy. And if you have much more massive stars above 10 solar masses or so, you're going to get much more supernova feedback and significantly more metal enrichment. So how do both of those changes impact how the simulations compare to observables? Here, once again, I'm showing you the star formation rate on the x-axis versus the oxygen-3 to carbon-2 luminosity on the y-axis. The simulations at different redshifts are shown by the color lines. And once again, this is the plot we had before, where if you just assume the solar abundances and the standard Krupa IMF, you can see we drastically underproduce the observations. However, if you just flip the assumption of solar abundances to core collapse supernova abundances, you can see that the simulations are in fairly good agreement with observations. And then the final plot shows if you assume core collapse supernova abundances, but you enhance the metallicity by a factor of 4, which would be consistent with assuming a much more top-heavy IMF, you can see once again that there's good agreement between the simulations and observations. Now, looking individually at the metal line abundances, so here we have carbon-2 luminosity in the top row versus the star formation rate on the x-axis, and oxygen-3 luminosity in the bottom row versus the star formation rate. Once again, if we have our original panels where the solar abundance model had good agreement between carbon-2 luminosity versus star formation rate, but we significantly underproduced the oxygen-3 compared to the star formation rate. Now, the middle panel, this shows the regime where we choose core collapse supernova abundances rather than solar abundances. Here you can see that because the carbon abundance has dropped, we're now in worse agreement with observations than we were before. However, we have a mild increase in the oxygen-3 luminosities, which allows us to get slightly closer to observations. However, if we combine both effects, where we once again assume core collapse supernova abundances and a 4 times enhanced metallicity, which would be consistent with a more top-heavy IMF, you can see now we're in a regime where there's slightly better agreement between the simulation and observations in the carbon-2 SFR relation. But now if you look at the oxygen-3 SFR relation, there's significantly better agreement. So all this to say, I will leave you with my conclusions that the physics of carbon-2 and oxygen-3 is highly complex. It depends on many galaxy properties such as density, metallicity, ionization parameter, escape fraction, et cetera. For this reason, you really need numerical simulations that try to capture all of these effects. And Sphinx 20, I think, is pretty good for that. It's of course not perfect, but it comes fairly close. And finally, we think that the carbon-2 luminosities and oxygen-3 luminosities that we see in high redshift galaxies, these galaxies are between 6 and 9. According to our simulations, they seem to point to a more top-heavy initial mass function and non-solar abundance patterns. So thank you.
Great, right on time. Thanks, Harley. Please post your questions onto the Slack channel. Oh, I see that Maxime's got his hand up on Zoom. So do you want to ask your question in person, Maxime?
I think I was just applauding, but great talk, I guess.
Thanks, Maxime.
Sorry, misrepresented the emoji. Okay, we've got some questions coming in. Laura Somovigo has asked, instead of tweaking the assumptions to reproduce the data, would it be possible to find a correlation with your low O3 luminosities with other galaxy properties from simulations? For example, are your simulated galaxies less bursty than the observed ones?
I mean, I'm not sure I fully understand the question, but from observations, it's hard to tell the burstiness of star formation because we don't have the star formation histories of these galaxies. Our galaxies do have very bursty star formation histories, so I don't think it's that. What we did in the paper is we systematically went through every single effect that we could find to try to figure out which physics could actually impact the oxygen-3 to carbon-2 ratios. We found things like the galaxies which had much higher ionization parameters had higher O3 to C2 ratios, galaxies with higher Lyman continuum escape fractions had higher, but basically there was nothing, as a general population, there was nothing that could get us that order of magnitude shift that you needed. So the point that we made is that if the galaxies that we have seen are representative of the high redshift universe, we would really need to do something like go to non-solar abundance patterns or push to a more top-heavy IMF. If, on the other hand, the galaxies that we've observed are observationally biased, that this is a point we make in the paper, then we do have a couple galaxies which end up in that regime, but it's certainly not representative of the bulk of the galaxy population. So in summary, we need more observations.
Great. Thanks. One more question from Daniel Ceverino. When computing line luminosities, are you assuming a clumping factor that takes into account the unresolved high densities where this emission is coming from?
Yeah, it's a good question. We didn't assume any additional clumping factor. I mean, at 10 parsec resolution at redshift 6, and it's significantly higher at high redshifts, we think we do a pretty good job. Especially for oxygen 3, most of the emission comes at densities that we actually resolve. With carbon 2, because it's at the much higher density regime, of course, there's subgrid clumping, and where this really comes into account is self-absorption for carbon 2. We find that itself could be a 50% impact, but unfortunately that only impacts carbon 2. It doesn't impact the absolute oxygen 3 luminosity. So if you did add a subgrid clumping, it would potentially reduce some of the carbon 2, but it's not going to push us any closer to where we need to be.
Great, thank you, Harley. You have got a couple more questions on the Slack if you want to answer them directly there, but we will move on to our next speaker. So Guochao Sun, or Jason, is from Caltech. Bring up your slides.
All right, thanks, Christopher. Can you see my screen now? Okay.
It looks good, take it away.
Cool. Right. Oh, okay. So hello, everyone. My name is Jason, and I'm a final year graduate student from Caltech. It's my great pleasure today to provide you with a quick introduction to LIMFAST, a semi-numerical toolkit that we're developing for studies of cosmological evolution of high-redshift galaxies using the technique of multi-tracer line intensity mapping. So we have already heard from Rahul earlier for some like exciting prospect for multi-tracer intensity mapping of the EOR from a numerical simulation perspective. And now I'll provide you with a semi-numerical view of this same theme. So inspired and pioneered by the 21 centimeter cosmology, line intensity mapping, or LIM, has become an increasingly popular tool to study reionization. And here's a demonstration of the basic idea for line intensity mapping measurement, which use moderate spatial and spectral resolutions to map the aggregate line emission without resolving individual line emitters. And so by comparing the 2D projected halo density field to the corresponding line intensity map, we can see that as a result of not resolving individual sources, the line intensity map is like a smeared version of the halo distribution. And this makes the measurement sensitive to not just the bright galaxies, but instead the entire source population, including dwarf galaxies and even diffuse emission around galaxies. And as I already mentioned, important motivation for our work is that line intensity mapping with multiple tracers has become an emerging frontier in EOR research. And so far, a good number of EOR line intensity mapping experiments targeting at different emission lines have been proposed and executed. This includes the best studied 21 centimeter line and several other lines like the 158 micron C2 line and rotational CO lines. And as shown in this left figure, from a recent science forecast paper for the time experiment for C2, these far infrared lines trace the ionization field in general, which can by themselves constrain the EOR history. But most importantly, these star formation tracers provide complementary information to the 21 centimeter signal. This can be easily seen from the right figure, where the top panel shows the C2 intensity field, and the bottom panel shows the 21 centimeter signal in two different scenarios of reionization. Some additional considerations include the achievement of a better foreground control through cross-correlations and the potentials to be combined with other probes of large-scale structures, such as galaxy surveys and CMB lensing or spectral distortions. Okay, so we heard about a lot of exciting progress from the simulation world, but an important point I'd like to make about the study of reionization and high-redshift galaxies is that simple models actually work better than one might naively think. Well, this is in part due to the lack of observational constraints at high redshift. The fact that high redshift galaxy formation and evolution are governed by relatively simpler physics is also an important reason. So even though detailed numerical simulations, have become a powerful mainstream approach, the promises of simple analytic models should still be recognized and fulfilled. And as an example, this left figure shows that galaxy luminosity functions about redshift 6 can be pretty accurately captured by a simple physical model based on smooth accretion onto dark matter halos and some star formation efficiency regulated by stellar feedback. So the idea of using a fewer number of free parameters to provide a clear picture of the essential physics while being flexible enough and portable enough to make a range of testable predictions is further illustrated in this right figure, which shows this space of astrophysical parameters in the galaxy model used in 21 centimeter MC. So basically the advantage of simple galaxy model motivate the development of LIMFAST as a handy tool to effectively extract astrophysical and cosmological information from not just the forthcoming intensity mapping dataset, but also their synergies with other probes. So here I'm showing you a flowchart explaining how LIMFAST stems from its parent code 21 centimeter fast with a significantly improved model of galaxy formation. So features that are shared in common with the 21 centimeter fast code include the 2LPT and the excursion set formalism used to describe the large-scale structure and the partitioning of mass into dark matter halos. And the updated galaxy formation model introduced is based on it's based on the halo growth history derived from abundance matching the halo number densities across redshift, which is then supplied to a quasi-equilibrium description of the stellar and gas component of galaxies maintained by like a balance between star formation and feedback. The set of halo properties derived from the quasi-equilibrium model are then coupled to a model of gas nebula through stellar population synthesis. And the emission spectrum is then simulated by photoionization code Cloudy. The resulting luminosity halo mass relation is then combined with the density field to produce the line intensity mapping signals of interest. So for the galaxy model, we consider variations of feedback mode and star formation law to understand how they can be probed by multi-tracer line intensity mapping. So to see that, let's first take a look at how the halo properties change. The left figure shows the redshift and mass dependence of various halo properties, such as gas mass and stellar mass. From the lower panel, we can see that switching between the momentum and energy-driven feedback result in different halo mass dependence of gas and stellar mass. Whereas the green and yellow curves shows that from the green and yellow curves, we can see that changing the star formation law can significantly vary the gas content, but barely changes the stellar mass. And this is because the star formation law only determines how efficiently stars form out of the gas reservoir, but hardly affect the total amount of stars formed. And the influence of feedback, on the other hand, is illustrated in this right plot that shows how the ratio of stellar mass and halo mass, or their time derivatives, look like under different strength of feedback regulation. And we can see that with a stronger feedback, there will be a steeper gradient with mass, and therefore more suppression of star formation in low mass halos. In terms of line luminosities implied by our galaxy model, here's how the C2 and CO lines scale with the star formation rate. And we can see that the luminosity SFR relation does depend on the feedback and star formation law in particular, because of the strong dependence of the gas content of these two lines. So it's clear that these poorly constrained relations could be useful probes of galaxy astrophysics at high redshift. However, an important caveat here is that there can be substantial degeneracies with other subgrid astrophysics, especially physical conditions of the interstellar medium, such as the gas density and the strength of interstellar radiation field. And at this point, we have to put them in by hand because they're not yet captured by our model. And this is an important aspect that can be improved for our future studies. So okay, now let's take a look at some snapshots from our simulation to understand the effect of stellar feedback on the EOR and the associated line intensity mapping signals. So here on the left, we show the 21 centimeter signal at different stages of reionization in different feedback mode. Then on the right, we show the line intensity field of H-alpha, Lyman-alpha, and C2, corresponding to the middle row of on the left when the reionization is about half complete. Besides the most pronounced feature, which is the large-scale complementarity between the tracers of neutral gas and ionization field, one can also see many more detailed features such as the bubble size, the clumpiness, and also the redshift evolution, actually, but which is not like explicitly shown here. And to quantitatively understand how we can make use of these detailed features, we need to look at some summary statistics like the power spectrum. So here I'm showing the redshift evolution of different line power spectra with different like feedback prescriptions. The redshift is indicated by colors in different shade, and the 4 cases of feedback are distinguished by the different line styles. Also in the background, the gray lines indicate the Poisson noise limit to help compare the power spectrum shape. So from these comparisons, the most important takeaway is that more efficient stellar feedback regulation means the power spectrum will have stronger redshift evolution and be more Poisson noise dominated. Namely, a small number of bright sources will dominate the signal. This general trend is particularly obvious for the C2 and CO lines because of their higher sensitivity to metallicity. So these diagnostics of power spectrum shape and amplitude are useful probes of feedback mechanisms for galaxies during the EOR. Now let's take a look at another aspect of model variations, which is the star formation law. Here on the left, I'm showing the auto and cross power spectra of Lyman-alpha, C2, and CO with a 21 centimeter signal. So we can see that lines scaling with the ongoing star formation rate, such as the Lyman-alpha, will not be affected by the star formation law, whereas lines sensitive to the gas content, like C2 and CO, are ideal probes of it. So one thing to note specifically is that if one wants to use the cross-correlation signal to infer the bubble size, pretty much like what Rahul mentioned, the impact of galaxy astrophysics, like feedback and star formation law, must be properly understood. And so this point is shown explicitly in this right plot, where you can see a clear difference caused by using different star formation laws as represented by the field and empty sets of markers. So just a few more words on the future directions. One particular action item is to include continuum emission, such as the CIB and CMB. So as illustrated in this recent work, future near-infrared intensity mappers like SPHERE-X and CDIME will place some interesting constraint on the presence of population 3 star signals in the cosmic near-infrared background. However, component separation in these angular fluctuation measurement will be very difficult. So joint analysis with some kind of 3D galaxy or line intensity mapping surveys will be useful for improving the constraining power on the first stars. Okay, so in the interest of time, I think I'll just leave my summary slide here and take any questions you have. Thank you.
Thanks very much, Guochao. If anybody has any questions, please post them into the Slack channel. I can't see any questions yet. We'll just wait a couple of seconds. Okay, got a question come in from Caroline Haneka. Hi, Jason. Interesting setup. Looking at Lyman-alpha maps / spectra, emission does by eye not look more extended / spectra seem to scale similar to, for example, H-alpha, making me curious about your Lyman-alpha implementation. Did you include extended IGM contributions for it?
Yes, we do. So we do have like a recombination component, which is diffused from the ionized IGM. So I think the effect is most obvious in this case of strong feedback, where you can see, compare with, say, the H-alpha field, which is kind of like compact, you do see like this extended component here in the case of Lyman-alpha, which is from the recombinations in the diffuse IGM.
Great, thanks. Wait for any more questions to come in. We've got 1 minute left. Okay, we've got a question from, I think it's Yuxiang Qin. How much variation do you expect if you use different PDR models to create lines, which is crucial for this joint constraint?
Yes, that's a very good question. So I actually, this is something we want to quantify in the near future, but my expectation is that the scatter or dispersion will be non-trivial because a lot of the subgrid astrophysics associated with the PDR that can be degenerate with the more galaxy scale astrophysics. So yeah, I mean, like many factors, like I mentioned, the gas density, the interstellar radiation field can all like affect the PDR region associated lines.
Okay, great, thanks. So if there's any more questions, please post them on the Slack and Guochao can answer them there. We're now going to move on to the next talk, which is by Yuxiang Qin. Yuxiang can't join us today, he's in Australia, so we've got a recorded talk, and I believe Ashwin is going to play that for me. He's got a copy of it. Are you there, Ashwin? There we go. So the talk is 15 minutes long, so there won't be any time for questions, and Yuxiang's not there to answer them directly anyway, but please post any questions on the Slack, and they will be able to get back to you tomorrow when they wake up. So yeah, take it away, Ashwin.
Hello, everyone. My name is Yuxiang Qin. I'm a postdoctor at the University of Melbourne. I want to thank the organizer for still having me to give this talk. But this is like 3:30 a.m. For me when you are seeing this video. So I do apologize for not being able to give this talk in person. But if you have any questions, please leave a message on Slack channel. I will get back to you in the morning. And this is the archive ID for the paper I'm presenting. So if you want to know more before I can get back to you, you can also check the paper. So this is the content of the presentation. I will spend half of the time talking about Lyman-alpha and the reionization. This sort of motivated this talk. And then I will show you the result from the Dragon simulation. So this plot shows you several light coincides between redshift 8 and redshift 5. So on the left, you have the density field. This is arguably well understood. So all we are trying to do is to come out with some prescription to convert the density field using bionic physics to get a galaxy catalog. And your catalog has to be calibrated against real observation. In most cases, this is galaxy stellar mass function or the UV luminal function. So once the catalog is consistent with observation, at least in a statistical way, this means that the model is well representative of the real universe. And then you can evaluate the UV background. Of course, you need to make some further assumption about the radiation property, in particular the UV ionizing escape fraction, which is not well constrained observationally. But if you have the UV background, you can evaluate the evolution of the temperature and also the neutral hydrogen fraction in the intergalactic medium. And with all of this information, you can estimate the Lyman-alpha transmission, which is a very important observable. You can obtain it by comparing the observed flux to the intrinsic one, which you can obtain from using some low redshift analog. And the reason we study Lyman-alpha transmission is because it can tell us the property of the galaxy that are responsible for driving reionization. For instance, if the UV background is dominated by more smaller halos, then the EOR morphology will be very different, and this will be reflected in the Lyman-alpha transmission. Okay, so you might have seen a different version of this plot already. This is a collection of the neutral hydrogen fraction constraint using Lyman-alpha observations. So on the left, you have the constraint using the Lyman-alpha forest. The published version is this McGraw et al. 2015. This is one of the observations that tells us UI has to finish at roughly 5.8, 5.9. But this is likely to be biased by cosmic variance. So we have more quasar observed since then. And please look, stay tuned for the latest updates from this SQR30 collaboration, where the analysis is has been redone using a more quasar spectrals. As study high redshift, you can either study the damping ring absorption using quasar spectra, which is shown here as the blue point, or you can study the Lyman-alpha emitter. You can study either their luminosity function evolution, or you can study the number of the fraction of galaxies that do show Lyman-alpha emission. So this is actually the focus of this talk. So if we look at this fraction between from redshift 3 to redshift 6, the fraction increases. This is likely due to a stronger star formation activity and increased escape fraction, which is more likely due to the fact that the environment is more pristine at high redshift. But if you go to even high redshift, the fraction decreases. This is predominantly because the universe is becoming much more neutral. However, some recent study at redshift 8 and also redshift 9 from this Laporte et al. 2021, they actually show a very high Lyman-alpha emitter fraction compared to the extrapolation where you use the data between redshift 6 and 8. So the reason they get such high Lyman-alpha fraction is because at such high redshift, you can really only obtain spectroscopy data using spectroscopy data for very bright galaxies. So for instance, this plot shows you the distribution of the Lyman break candidates at the redshift 8. These are the observed Lyman break galaxies with spectroscopy. And in fact, we have follow-up on 4 brightest galaxies at this redshift, and all of the 4 Lyman break galaxies are identified as Lyman-alpha emitters. So we also have some preliminary results with some Hubble follow-up. So you basically take an image around 3 out of the 4 Lyman-alpha emitters at the redshift 8. And the preliminary results actually found there are a lot of neighbors nearby the Lyman-alpha emitter. This is much higher than a random field. So in this work, we basically want to study why the transmission of the IGM is enhanced around the bright galaxies. So this comes to the Dragons project. So for those who haven't heard of it, it stands for Dark Ages Reionization and Galaxy Observables from Numerical Simulations. So the main component of the Dragons project is this miraculous semi-analytic model. So we basically build a halo merge tree by running some high-resolution embodied simulation, and then we apply the miraculous semi-analytic model on the top of that, so we can obtain a galaxy and also a quasar catalog. The model is well calibrated against the observed stellar mass function and also the galaxy UV luminosity function from the local universe all the way to redshift 10. This is just an example at low redshift where we switch on and switch off AGM feedback. So in this paper, which is the 20th in this series, and this is likely to be the last one because we are moving towards the next phase. But in this paper, we focus at redshift 8. This is the redshift where we observe 4 brightest Lyman galaxies using spectroscopy, and all of them show Lyman-alpha emission. So on the left, I'm showing you the density field. And on top of that, I'm showing you the location of the bright galaxies, so brighter than 27.5 in the Hubble H band. And you can see that those bright galaxies actually follows the density peak. So on the right hand side, I'm showing you the neutral hydrogen fraction. And so at this redshift, this model predicts 86% neutral fraction. It's worth noting that this model is consistent with the Planck measurements in terms of the CMB optical depth, and also the global neutral hydrogen fraction evolution is consistent with the Lyman-alpha observation constraint that I showed you before. So for the galaxy on the right-hand panel, I'm actually only showing you the galaxy that's considered as transparent in Lyman-alpha. So in other words, they will be observed as Lyman-alpha emitters. And you can see that they are either very bright or they are clustered together. So in this work, we consider a galaxy to be Lyman-alpha emitter when the damping absorption in the intergalactic medium, in addition to another factor of 2 absorption inside the H2 bubble, has to be weak. So by weak, I mean the total optical depth has to be smaller than 1. So this is how we define a Lyman-alpha, a transparent Lyman-alpha emitter in this work. To be more quantitatively, so this plot shows you the transmission as a function of the bubble size on the left, and also as a function of the density, which is smooth on some large scale on the right. So you can see that there's a strong correlation between the transmission and the bubble size. This is also well known. So this dashed line is a theoretical expectation for these two correlation when you assume this mean neutral hydrogen fraction. So this basically tells you that if the galaxy sits in a big bubble, its Lyman-alpha is able to redshift deep in the damping ring, so that the transmission is very high. So on the right side, this is a function of density, and so basically you can see the transmission is more likely to be high if the galaxy sits in overdense regions. And we are also plotting the galaxy based on whether they have satellites in the same H2 bubble. So if they do, this is the filled circle. They are preferentially sitting in high dense regions, and they are also more likely to be transparent. So in this study, we found for transparent Lyman-alpha emitter, which is above this gray strap, they are sitting in bubbles larger than 7 coulomb megaparsec at this redshift, and they sit in overdense regions. And also galaxies with satellites are more likely to have higher transmissions. So this seems to suggest that if you are going to identify Lyman-alpha emitter using spectroscopy, if you can pre-select those candidates using, for instance, a Hubble image, by only targeting at galaxies which has a lot of nearby galaxies, you will have more chance to find their Lyman-alpha emissions. I will come back to this later, but we can also study the correlation between the transmission as between the transmission and the galaxy property. So here I'm showing you the transmission as a function of the UV luminosity. And you can see, again, brighter galaxies, because they are more effective at ionizing the nearby neutral hydrogen, they sit in larger bubbles, which means that their Lyman-alpha redshift more, so that the IGM is more transmissive to them. So we also find that for galaxies brighter than 25.5, they seem to have a similar level of damping ring, and all of them are transparent in Lyman-alpha. This is obviously a small sample because we are limited by our box size, but this seems to be consistent with the observation that I mentioned at the beginning, that we observe 4 out of the brightest galaxy at redshift 8, and all of them show Lyman-alpha emission. So I also talk about the environment. So we can do the same thing in our simulation. Basically, we take the same field of view as the Hubble image, and we count the number of neighboring galaxies within the field of view. This is just to show you an example for 2 typical galaxies. And this plot shows you the number as a function of the luminosity. I'm only showing here for the brightest galaxies, and we found up to 7 nearby galaxies within the Hubble field in our mock image, and this is consistent with the preliminary results again that I mentioned at the beginning. So I just want to finish by commenting some of the next plan. So obviously, from the observational side, we want to confirm more high-redshift galaxies. Most of the current high-redshift galaxies only have photometric redshift. So I'm very proud to be to be part of this upcoming JWST program led by Pascal Osh. So we are going to use NearCam. So this is a mid-sized project, and we are going to use NearCam algorithm to obtain spectroscopy redshift for hundreds to thousands of galaxies at high redshift. And this will allow us to study better the distribution of those galaxies and also the morphology of reionization. And from the simulation side, we are extending the simulation to a larger box. But when you go to larger box, you become limited by the resolution. So we are using an algorithm developed by a former postdoc, Yuxiang Qin, which is now led by our PhD student, Balu Srida. And we use this algorithm to augment the on-body simulation so that we can effectively have a more than 1 trillion particle on-body simulation. And this will allow us to resolve atomic cooling galaxies in a simulation box of more than 300 Coumadin megaparsec. And this will allow us to have 10 times more bright galaxy sample in this kind of a study.
Okay, so yeah, thank you to Yuxiang in his absence. If you have any questions for Yuxiang, please post them on the Slack and he'll be able to get back to you there. We now move on to our final speaker for today, Thibault Garel from Geneva. Do you want to bring your slides up?
Okay, can you see my slide?
All looks good. Take it away.
Okay, perfect, thanks. Okay, so thanks for giving me the opportunity to present a paper about the evolution of Lyman-alpha emitters in Sphinx that we published a few months ago. So Sphinx is a cosmological radiation-hydrodynamics simulation of the high-redshift universe. And the main idea of this project was to post-process it with Lyman-alpha to see how the Lyman-alpha emitter population can be used as a probe of the Epoch of Reionization. So let me start with a quick introduction. So here I'm showing the reionization history, where we see the transition between a fully neutral state and a nearly completely ionized universe by redshift 5 or 6. In between, during the art of the Epoch of Reionization, most observational constraints come from Lyman-alpha emitters. So the basic idea behind these diagnostics is that LAEs become less visible towards higher redshifts, since Lyman-alpha photons produced in galaxies are more likely to be absorbed by the IGM as it becomes more and more neutral. So altogether, these observations show that there is certainly a rapid transition in the IGM state around redshift 6 or 7, but we can wonder if the observed evolution of LAEs is purely due to a change of the IGM neutral fraction. So indeed, there are many factors that can drive the visibility of LAEs, because Lyman-alpha transfer is a multiple scale problem, where photons are emitted in galaxies and can then resonantly scatter in the ISM and the CGM before being propagated through the intergalactic medium. So therefore, it's important to understand the evolution of internal Lyman-alpha processes in galaxies to disentangle the relative contributions of intrinsic Lyman-alpha emission, escape fraction, and IGM transmission. And this is particularly true at high redshift, where galaxy galaxies commonly exhibit inflows or outflows that can strongly affect the Lyman-alpha line that is emerging from galaxies. So to investigate these aspects, we use the Sphinx 10 simulation that we post-processed to perform end-to-end Lyman-alpha radiative transfer in thousands of galaxies between redshift 6 and 9. So here I'm listing some of the main features of Sphinx that Harley already presented a bit. So I'm not going to go through everything, but briefly, Sphinx is a set of RHD simulations run with the Ramses RT code, in which we can describe the production and propagation of radiation. So here we use the version with a 10 co-moving megaparsec box size, high physical resolution up to 10 parsec at redshift 6, and mass resolution that is sufficient to resolve dark matter halos at the atomic cooling limit. An important feature of this simulation is that we use the BPAS SED model, which includes binary stars. And as you can see here on the reionization history plot, our simulation predicts a pretty early reionization, which is mainly due to the inclusion of binary stars that can produce ionizing radiation over longer time scales and thus favor the escape of the Lyman continuum from galaxies, such that the universe is fully reionized in our simulation by redshift 6 or even 7. So for the Lyman-alpha transfer, we use the Raskas Monte Carlo code, and we follow basically 3 steps. So first, we predict the intrinsic emission from galaxies within the stellar radius, accounting for both Lyman-alpha photons produced by recombinations and collisions. Then the escape fraction is evaluated at the CGM radius, which is taken to be 10 times the stellar radius, and it roughly corresponds to the virial radius of the host dark matter halos. And finally, photons that escape the halos are propagated through the full box to compute the IGM Lyman-alpha transmission. So let's now compare some results with observations. So here I'm showing the UV luminosity functions at redshift 6, 7, 8, and 9. So the black lines are the predictions from Sphinx before and after dust attenuation, and the data points come from observations. So we find a fairly good agreement with observations at all redshifts. We note that we cannot predict the very bright end. That's because our volume is rather small, which implies that we simply don't have very massive or very bright galaxies in our simulation. And overall, we find a stronger effect of dust at the bright end compared to the faint end, simply because brighter galaxies are on average more massive, so they tend to have more gas and metals, and therefore have a higher dust opacity. So from there, we can now compare our predictions with some Lyman-alpha quantities. I'm going to start with the Lyman-alpha luminosity functions at redshift 6, 7, 8, and 9 again. So first, we show the intrinsic Lyman-alpha luminosity function with black dashed lines in each panel, and the dust attenuated LF with a solid black line, which corresponds to the luminosities after radiation transfer in the ISM and the CGM. We see that the dust attenuation suppresses the Lyman-alpha luminosity functions at all redshifts by about 0.5 to 1 dex. And next, if we include the effect of IGM transmission that gives the orange curves, we see that our luminosity function at z equals 6 roughly agrees with the faint end that is observed. That's the gray data points here. And overall, we find that the reduction of the Lyman-alpha luminosity function due to IGM is pretty small at redshift 6, say a factor 2, compared to the dust attenuated one. But it strongly increases at higher redshift, and it becomes even quite significant by redshift 9, with a shift of the luminosity function of almost 2 dex. Another way to see this is to look at the redshift evolution of the luminosity functions for the 3 cases, for intrinsic, after CGM transfer, and after IGM transfer. So from the left panels, we see almost no redshift evolution for the luminosity functions for the two first cases. But we note there is a strong variation if we include IGM transmission. So basically, the dust attenuated luminosity function does not evolve because we predict that the mean Lyman-alpha escape fraction does not change with redshift. And we find that it's about 3 times higher on average for faint galaxies compared to bright galaxies. Instead, the global IGM transmission significantly decreases with redshift by almost a factor 10 between redshift 6 and 9, which corresponds to the period where the universe becomes more neutral. So another common probe of reionization is the LIE fraction, which basically measures the fraction of UV selected galaxies with Lyman-alpha emission. So here again, we computed for the 3 cases using only the intrinsic Lyman-alpha equivalent weights, then accounting for the escape fraction, and finally also including the IGM transmission. Overall, we find that the LIE fraction computed from intrinsic and dust attenuated properties remain constant with redshift. That's the black lines on the plot. It is only when we account for IGM that we see a drop of the Lyman-alpha emitter fraction in orange. So we can note that the drop is actually a bit too early compared to observations. So if instead we shift it by a delta Z of about 1, that's the purple line, we find a much better agreement. And actually it turns out that this offset is a consequence of Sphinx probably reionizing the universe a bit too early. You can see it here on the reionization history, where we find a delta Z of about 1 compared to the observational constraints. So the main message here is that the XLAE is tracing the evolution of the neutral state of the universe, but we can note that it's somehow a weak tracer because XLAE varies only by a factor 10 between redshift 6 and 9, whereas the neutral fraction varies by a factor 10,000 almost. So we can now move on to and look a bit more closely at the internal properties of Sphinx galaxies. So here, as an example, I'm showing the H1 density maps at the CGM scale and the ISM scales for 2 galaxies, one massive and one less massive. We see on these images that the gas distribution at small scales is very complex, which is especially due to the presence of strong inflows or outflows. And these gas flows are very important in terms of Lyman-alpha transfer because they can strongly alter the line profile before it enters the intergalactic medium. So let's look at some Lyman-alpha spectra that we predict. Here I'm showing median angle average spectra per beam of redshift and per beam of UV magnitude. So basically, in each panel, we see the intrinsic mean line profiles produced in galaxies and the mean spectra after escape from galaxies in a black solid line. So we can note a few things from these plots. First, there is no strong redshift evolution, but we see a clear trend with UV magnitude. So for faint galaxies on the left, spectra after transfer are almost symmetric with 2 peaks, whereas for UV bright galaxies on the right side, they become more single-peaked and red dominated, which is likely due to the presence of outflows that can redshift a bit Lyman-alpha photons from resonance. And interestingly, in all cases, we see that the red peak is located at about 150 kilometers per second, which is the typical value which is measured in high redshift Lyman-alpha emitters.
1 minute.
Yeah, I'm almost done. So finally, we can add also the effect of IGM transmission that gives the orange spectra. So we see that only red photons can be transmitted, except at z equals 6, when the universe is very ionized, where some blue photons can be transmitted. And looking at the redshift evolution, as expected, we find that the suppression of the red side increases towards higher redshift. But even at redshift 8 or 9, when the universe is very neutral, part of the line can still be transmitted on the red side. So we can look at the variation of the IGM transmission with frequency, which was also discussed in Aaron's talk. So here we show the mean IGM transmission as a function of rest frame wavelengths. So while the blue side is nearly always suppressed, we see that the red transmission is a strong function of the velocity offset, so such that the red transmission will completely dominate the overall Lyman-alpha transmission of the IGM. So that means that depending on the shift of the Lyman-alpha line after transfer in galaxies, the fraction of the Lyman-alpha flux transmitted by the IGM can be very different. And basically it means that the visibility of LEs during reionization is strongly dominated by both the shape and offset of the line after internal radiation transfer. And just to finish up, I'm showing here a simple toy model where the Lyman-alpha line after CGM transfer is described by two parameters, the velocity offset and the width of the line. And when we apply the IGM transmission, depending on the line parameters, we see that the IGM transmission can induce very large variations in the Lyman-alpha luminosity function from, say, 0.5 dex at redshift 6 up to almost 2 dex at redshift 9. And I will leave my concluding remarks here. Thanks.
Great, thanks very much, Thibault. We have time maybe for just one question. Just run out of time a little bit. If there's any quick questions on the Slack, please post them now. Okay, we've got one from Aaron Smith. Really great work. I'll limit my questions. Have you checked that the Lyman-alpha emission predicted by the RHD simulation is consistent with the expectation from stars?
You mean that the case B recombination Lyman-alpha emission agrees with predictions from star formation rate? You mean?
Yeah. So specifically, if you take the ionization states from the like M1 method, because there's complications with the thermochemistry and all these types of things, if you perform like a ray tracing post-processing ionization calculation again, then this will actually differ from the prediction from these simulations. I mean, obviously I have not checked this in your simulations, but for example, in the context of smuggle or fire simulations, these disagree.
Okay, I don't think it's the case for our simulation, but I haven't checked, so yeah. Can't really tell you, sorry.
There is one more question. I'll just read it out now because we've got nothing coming up to it. It's from Anne Hutter. She says, why would outflows play a more important role in bright than in faint galaxies?
That's a good point.
She's thinking of low mass galaxies being more disrupted by feedback.
Yeah, that's a good point. So I haven't looked in details at inflows and outflows in low mass and high mass galaxies in much details, but that's a very good point. I think one reason is that low mass galaxies are maybe in regions where they are completely dominated by gas inflows because they are small, so they lie within filaments where they are fully enclosed in infalling gas. But that's a good point, and that's not really what I was expecting at first when I saw these spectra and the evolution with luminosity or mass.
Okay, great, thanks. We'll finish there. So I just want to say a thank you to everybody who stayed until the very end today, and thank you to all of our speakers in this session. We will all reconvene tomorrow for 2 more sessions of this SAZERAC SIP. And yeah, hopefully see you all there.
Thank you, Chris, for chairing this section. I'll see you all tomorrow.